Damos inicio a la ceremonia de lanzamiento del Atacama Desert Vaccine Laboratory at Balab y al Simposio de Inmunología en Primavera en el desierto de Atacama, desde la Edad Media del COVID-19 al renacimiento por la vacunación. Saludamos a las autoridades que hoy nos acompañan. Señor Vicerrector de Investigación, Innovación y Posgrado de la Universidad de Antofagasta, doctor Rodrigo Iturriaga. Honorable Diputado, señor José Miguel Castro. Director del FIC Protección, Creación del Atacama Desert Vaccine Laboratory en Antofagasta, doctor Cristian Muñoz. Señor Jorge Orellana, quien asiste en representación del señor Gobernador. Jefa de División de Fomento e Industria del Gobierno Regional de Antofagasta, señora Gabriela Gómez. Señor Director Alterno del Instituto Milenio de Inmunología e Inmunoterapia, doctor Leandro Carreño. Comunidad universitaria, señoras y señores. Tengan todos muy buenos días. La Universidad de Antofagasta se complace en darles la bienvenida al seminario Simposio de Inmunología en Primavera en el desierto de Atacama, desde la Edad Media de COVID-19 al renacimiento por la vacunación. Esta actividad es desarrollada en el contexto del proyecto FIC-R, del proyecto FIC-R 2017, Protección, Creación del Atacama Desert Vaccine Laboratory en Antofagasta, ideado y ejecutado por esta Casa de Estudios Superiores con el aporte financiero del Gobierno regional, en colaboración con el Instituto Milenio de Inmunología e Inmunoterapia y la Pontificia Universidad Católica de Chile. El Atacama Desert Vaccine Laboratory es un proyecto de la Universidad de Antofagasta que consiste en la creación de un laboratorio de investigación, desarrollo e innovación en tecnologías para vacunas y productos biotecnológicos biomédicos. Esta iniciativa es parte de una contribución en el ámbito de la innovación para diversificar la economía de la región a través de la biotecnología aplicada a la biomedicina. Para dar inicio al lanzamiento del Atacama Desert Vaccine Laboratory, se dirigirá a ustedes en representación del rector de la Universidad de Antofagasta, doctor Marcos Sikutovich Salas, el vicerrector de Investigación, Innovación y Posgrado de la Universidad de Antofagasta, doctor Rodrigo Iturriaga Aguirre.
Estimadas autoridades regionales, universitarias, todos miembros de la comunidad de la Universidad de Antofagasta, señor José Miguel Castro, diputado por Antofagasta, señor Jorge Orellana, señora Gabriela Méndez, Leandro Carreño. Me es muy grato, en nombre de la universidad y del rector, decir estas palabras con ocasión del lanzamiento del Atacama Desert Vaccine Laboratory y de este simposio de inmunología en primavera en el desierto de Atacama. La creación de este laboratorio es el resultado de este proyecto, tal como se nombró, que nace de la colaboración de académicos y académicas de esta universidad con el Instituto Milenio, Inmunología y Inmunoterapia y la Universidad Católica de Chile. Y, como se dijo, este proyecto se desarrolla con el apoyo del gobierno regional de Antofagasta. Hacer ciencia y generar conocimiento que se pueda traspasar a la sociedad civil es uno de los principales pilares del Plan de Estrategia Regional de Innovación del Gobierno Regional. Para hacer investigaciones en las regiones no es fácil y requiere de un gran esfuerzo de todo. No hay duda que cuanto más alejado de Santiago, más difícil es hacerlo. Y a esto hay que agregar que las regiones del norte están más desprotegidas. Esto no lo dije yo, lo dijo la actual ministra de Ciencia. Nos reunimos los vicerrectores en Concepción el miércoles de la semana pasada y ella se dirigió a los vicerrectores diciendo que las universidades de regiones son muy importantes y particularmente las del norte, porque las del sur parecen estar, a pesar de estar lejos de Santiago, más cerca. Sin duda este simposio es importante para nosotros y hoy podemos ver y vamos a escuchar la contribución de destacados científicos y científicas de renombre mundial en temas de inmunología. A todas ellas y ellos le agradecemos su presencia. La creación del Atacama Desert Vaccine Laboratory como plataforma para la investigación y desarrollo de vacunas y productos biotecnológicos biomédicos es clave para el desarrollo regional. Esta plataforma de investigación básica a través de pruebas preclínicas va a permitir desarrollar en un futuro cercano vacunas, biofármacos, etc., contribuyendo a la innovación y a la diversificación económica de la región, con un foco en la biotecnología con aplicación biomédica. Y esto recalco que es uno de los principales pilares del desarrollo que la universidad quiere contribuir. Durante el desarrollo de este proyecto, los investigadores han contribuido a mitigar los efectos de la pandemia del COVID. Se han establecido colaboraciones con el Ministerio de Salud en la logística, distribución de vacunas, estudios clínicos para evaluar la eficacia y la respuesta inmune de vacunas contra COVID en la población pediátrica. Hay un enorme esfuerzo también en realizar PCR y poder seguir esto. La Universidad de Antofagasta, a través de este vicerrector, declara su interés y compromiso para que este trabajo no sea en vano y que a través de la creación del Centro de Investigación en Inmunología y Biotecnología Médica de Antofagasta, que va a ser uno de los pilares más importantes, podamos crear un doctorado en Ciencias Biológicas y Biotecnología en áreas extremas. Finalmente, quiero agradecer la presencia de colaboradores cercanos, Claudia Velasco Sea de Cercal, Miriam Sperer, gerenta de ventas BD, y al doctor Carlos Calderón, director de investigación de la Universidad Católica del Norte, por el apoyo que han brindado a este proyecto. Siempre uno escucha al vicerrector o al rector. El take home message, lo que tienen que llevarse para la casa, es que aquí existe la posibilidad de desarrollar ciencia, y esa ciencia que desarrollemos tiene que formar parte de lo que las universidades de la región hagan en un pregrado o posgrado continuo, pero que tiene que tener un compromiso también a nivel regional con lo que hace esta región. Y eso es importante, y eso no se va a poder hacer solamente la universidad. Necesita el apoyo, por un lado, de la industria, pero también el apoyo de los gobiernos regionales y del Estado de Chile. Muchas gracias.
Agradecemos las palabras del vicerrector. A continuación, y en representación del señor gobernador regional Ricardo Díaz Cortés, se dirigirá a ustedes el señor Jorge Orellana, jefe de la División de Administración del Gobierno Regional de Antofagasta.
En primer lugar, muy buenos días a todos y a todas, especialmente a los estudiantes que están acá presentes, a nuestra autoridad, el diputado Castro, el vicerrector de la Universidad de Antofagasta, Centro de Investigación de la UBA, Instituto Milenio también, que está por acá con nosotros. Quisiera en primer lugar entregarles el saludo fraternal, como siempre, digamos, de parte de nuestro gobernador Ricardo Díaz a la Universidad de Antofagasta. Nosotros como gobierno regional tenemos una especie de alianza ya de trabajo histórico con esta universidad pública y entendemos que la alianza con el sector público, con nuestras universidades, es fundamental para el desarrollo de nuestra región. Una de las realidades que estamos intentando superar como gobierno regional es que el gobierno regional pase de ser un organismo de transferencia de recursos económicos para gasto a un organismo del gobierno regional representativo de toda la ciudadanía que se transforma en un organismo de transferencia de recursos para inversión. Ese es uno de los grandes desafíos que tenemos nosotros como gobierno regional en materia de destinación de recursos financieros que son de todos los chilenos para el desarrollo de nuestra región de manera descentralizada. Y en ese contexto nos interesa mucho, de hecho hemos dado prueba de eso, tenemos un proyecto con la Universidad de Antofagasta de aproximadamente 1.000 millones de pesos, ¿no es cierto?, que estamos pronto a terminar en el mes de marzo del año 2023. Y una de las cosas que yo quisiera señalar en esta ocasión es que la ciudadanía se convence más de la justificación del mundo público, no solamente cuando ve promesas o información, sino que cuando ve productos, cuando ve realidades. La ciudadanía entiende, por ejemplo, el proceso de descentralización cuando esta descentralización llega a las comunas con hechos concretos. Entonces, el estímulo, la motivación, el llamado que queremos hacer como gobierno regional es que aquellos recursos que transfiramos a distintos organismos, sean estos públicos o privados, puedan, en el tiempo que corresponde, mostrar los productos que la gente necesita ver. Yo creo y creemos nosotros que cuando la región de Antofagasta vea el laboratorio ya produciendo aquella vacuna, la situación va a ser distinta y el escenario va a cambiar y tal vez la percepción también va a ser distinta respecto a la comunidad en cuanto a la transferencia de recursos que nosotros le entregamos a nuestras organizaciones que nos apoyan en el desarrollo de distintos proyectos que van en bien del desarrollo de nuestra región. Eso en primer lugar. Y en segundo lugar, decir algunas palabras también con este gran tema que es el de la investigación y de la ciencia. Es súper fundamental. Chile tiene grandes brechas y naturalmente cuando se elabora el presupuesto, diputado, las principales preocupaciones, vivienda, salud, educación, inmigración, seguridad, probablemente. Son las necesidades fundamentales para un país para que se pueda autocomprender como un país desarrollado la superación de esas principales brechas que tienen un impacto social gigantesco. Pero eso significa que tenemos que dejar atrás o secundariamente la ciencia y la investigación. Eso no es así. Los países realmente se desarrollan cuando hay ciencia y cuando hay investigación, cuando hay incorporación de tecnología a los procesos productivos, por ejemplo. De tal manera de que es súper importante contar y seguir contando con la colaboración de nuestras universidades públicas y también de las universidades privadas y de todos los organismos que tengan como visión contribuir al desarrollo integral de nuestra región de manera sustentable, como muchas veces lo ha dicho nuestro gobernador. Nuestro compromiso es con nuestras universidades, es con nuestra región. ¿Por qué? Porque efectivamente nosotros estamos convencidos de dos cosas. Y en eso estamos muy convencidos. Tenemos la materia prima para hacer investigación, el sol, la luz solar. Tenemos el litio, tenemos la materia prima aquí en nuestro territorio para hacer investigación científica. Y lo otro que es muy importante, tenemos el recurso humano, los científicos. Por algo se está pensando en la Universidad de Antofagasta en levantar doctorados y más doctorados para que la gente de nuestra región alcance los estándares de otras universidades del país que también tienen altos grados de estándares en materia de investigación científica, como algunas universidades de la región metropolitana e incluso universidades a nivel internacional. Así que nuestro convencimiento como gobierno regional, nuestro sentimiento también en representación del gobernador regional es entregarle todo el apoyo que sea necesario para poder seguir avanzando en el desarrollo integral de nuestra región de Antofagasta de manera armónica y sustentable, como lo dice nuestra Estrategia Regional de Desarrollo. Muchas gracias.
Agradecemos las palabras del señor Orellana. A continuación, se dirigirá a ustedes el director del Atacama Desert Vaccine Laboratory, doctor Cristian Muñoz.
Bueno, primero, señores autoridades de gobierno, autoridades de la Universidad de Antofagasta, estimados invitados y estimada comunidad universitaria, tengan todos ustedes muy buenos días. Tal como decía el señor vicerrector y el representante, ¿cierto?, del gobernador, del señor Ricardo Díaz, ¿cierto?, hacer ciencia desde el norte, desde un polo, ¿cierto?, que no es el centro del país, es totalmente complejo, es difícil. Siempre hay que ir remando contra la corriente. Este proyecto de protección-creación del Atacama Desert Vaccine Laboratory es un proyecto que a nosotros nos permite crecer desde las bases, ¿cierto?, de generar nuevas plataformas, y estas plataformas, ¿cierto?, desde la universidad pública, que van a permitir contribuir al desarrollo de la ciencia desde el norte para el país, ¿ya? Nos va a permitir contribuir en desarrollar a nuestros estudiantes de pre y también en el futuro nuestros estudiantes de posgrado, ¿cierto? Y estas plataformas que con tanto esfuerzo nosotros logramos levantar aquí, hoy día se están haciendo una realidad. Hoy día partimos con el puntapié inicial, ¿cierto?, para la comunidad de Antofagasta, de tener un primer laboratorio, ¿cierto?, denominado Atacama Desert Vaccine Laboratory, ¿ya?, que va a dar respuestas a todas las interrogantes que nosotros tengamos como región, ¿ya? Y esto para nosotros ha sido extremadamente relevante y satisfactorio también a la vez, ¿cierto?, poder presentar esto hoy en día a todos ustedes mediante este simposio también que se está realizando con importantes invitados de carácter nacional y también de internacional, que después de unos largos procesos de pandemia, finalmente nos permite reunirnos para conversar de ciencia, para discutir de ciencia. Y eso para nosotros es muy satisfactorio, nos pone muy felices, y todo esto que nosotros preparamos para ustedes, agradecemos infinitamente al apoyo irrestricto que hemos tenido del gobierno regional por haber confiado en nosotros, y también a nuestras autoridades de la universidad, y por supuesto a los que finalmente también hacen esto, que muchas veces uno no los menciona, que son nuestros estudiantes, ¿ya?, que colaboran con la ciencia, ¿ya?, que nos ayudan a publicar, que nos ayudan a avanzar en la investigación y desarrollo que nosotros queremos para nuestro norte. Eso, ¿cierto?, les quería mencionar. Tengan ustedes un muy buen día y muchas gracias por estar aquí con nosotros.
Agradecemos las palabras del doctor Muñoz. Para continuar, se dirigirá a ustedes la directora del área de infecciones del Instituto Milenio en Inmunología e Inmunoterapia, doctora Susan Buena.
Bueno, autoridades regionales, don José Miguel Castro, diputado, muchas gracias. Representantes del gobernador, don Jorge Orellana. Autoridades universitarias, vicerrector de Investigación, Innovación y Posgrado, el doctor Rodrigo Iturriaga. Director de Gestión e Investigación, doctor Carlos Portillo. Doctor Cristian Muñoz, director del proyecto FIC-R 2017. Doctora Margarita Lay, directora del Centro de Investigación en Inmunología y Biotecnología Biomédica de Antofagasta. Colaboradores de la Universidad de Antofagasta. Nuestros colaboradores extranjeros que hoy día nos acompañan, amigos y amigas. Primero que todo quisiera darles una cordial bienvenida a esta actividad. Iniciar esta presentación, por supuesto, agradeciéndoles la asistencia y comentarles que estamos celebrando hoy varias cosas, entre ellas un logro muy importante de un proyecto colaborativo, cuyo principal objetivo es incentivar el desarrollo de la inmunología a lo largo de Chile, que ha sido uno de los objetivos que se ha planteado el Instituto Milenio en Inmunología e Inmunoterapia, de incentivar el desarrollo de la inmunología no solamente en Santiago, sino que en todo Chile. Esto se ha gestado por más de 10 años. De hecho, esta colaboración que estamos hoy celebrando en Antofagasta ha sido liderada en un comienzo por los doctores Margarita Lay, que hoy nos acompaña, y el doctor Alexis Calergis, director del Instituto Milenio en Inmunología e Inmunoterapia, apoyado por este instituto, y en el cual se ha sumado académicas y académicos de varias universidades para poder hacer crecer esta iniciativa. Investigadores de la Universidad de Antofagasta, por supuesto, de la Universidad Católica y de la Universidad de Chile. No quisiera continuar sin transmitirle las excusas del doctor Alexis Calergis, quien debió postergar su viaje por una reunión muy importante que tiene por objetivos de avanzar justamente hacia los objetivos de este proyecto. Pero que gracias a que somos un equipo muy afiatado, los que trabajamos en el Instituto Milenio y con nuestros colaboradores, nos ha permitido que otros podamos inaugurar este evento hoy y hacer extensiva nuestra alegría como instituto de participar en este gran hito. Esto es importante indicarles que en torno a esta iniciativa se han generado varios convenios de colaboración entre las universidades participantes y que han permitido el intercambio de estudiantes y colaboración activa en nuestros grupos de investigación. Hemos logrado tener publicaciones conjuntas, estudiantes en conjunto, tesis en conjunto y también, por supuesto, proyectos de investigación. Hemos también explorado colaboraciones con el Estado y con empresas que hacen I+D en vacunas. Esta iniciativa, por supuesto, ha abierto espacios para que tesistas jóvenes de Antofagasta puedan hacer sus tesis o parte de sus tesis en Santiago, lo que ha estrechado aún más nuestros lazos de colaboración y tal como decía el doctor Cristian Muñoz, si los estudiantes, que son, digamos, la semilla y el insumo para que estas colaboraciones crezcan y la ciencia crezca y desarrollemos nuestro país, esto no sería posible. Esta iniciativa también quisiera agradecer el invaluable apoyo del gobierno regional y las autoridades legislativas, que han sido fundamentales para el éxito de esta importante iniciativa colaborativa. Actualmente estamos avanzando sostenidamente en la generación de un laboratorio de I+D avanzado en esta región, que se complementa también con otras iniciativas en las cuales participa el Instituto Milenio en Inmunología e Inmunoterapia, como un laboratorio de buenas prácticas de manufactura de vacunas que se encuentra construido en el Centro de Innovación Anacleto Angelini de la Universidad Católica en Santiago. Quisiera finalmente destacar la creación de capacidades para estudios científico-clínicos en la región, que es algo que realmente nosotros valoramos y atesoramos muchísimo, porque considero que es uno de los grandes logros que hemos tenido justamente en pandemia, en el que participó el Hospital Clínico de la Universidad de Antofagasta y nuestros colaboradores. Estos estudios entre la Universidad de Antofagasta, la Universidad Católica y el Instituto Milenio de Inmunología e Inmunoterapia, junto con el Hospital Clínico, contribuyeron a la vacunación de la población infantil de Chile y de otros países y ha permitido controlar gradualmente la pandemia que nos ha golpeado tan duramente, que es la COVID-19. Quisiera concluir agradeciendo a los doctores Retamal y Cárdenas, Ángelo Retamal y Antonio Cárdenas, así como a los equipos que ellos lideraron durante la ejecución de un estudio científico clínico para evaluar la vacuna inactivada CoronaVac en población infantil en Antofagasta, creando por primera vez capacidades y realmente estuvieron a la altura de los centros más especializados que tenemos en Chile y hemos logrado tener resultados muy importantes. Y también quisiera agradecer a nuestros colaboradores internacionales que han viajado desde diversos países del mundo para acompañarnos hoy en este especial momento. Thank you very much, our collaborators, for traveling to Antofagasta from different parts of the world to become part of this important moment for us. Sin esto, me despido y muchísimas gracias y espero también que puedan apreciar y puedan participar activamente en los seminarios científicos que son parte del Spring Immunology Symposium en el desierto de Atacama. Muchas gracias.
Agradecemos las palabras de la doctora Bueno. Invitamos entonces a continuación a dirigir unas palabras a los presentes al diputado señor José Miguel Castro.
Hola, tengan todos muy buenos días. Es un tremendo orgullo estar acá por segunda vez en este podio. La primera vez estábamos hablando de una planta de vacunas, teníamos a 3 ministros de Estado, estuvimos con las autoridades regionales, con la universidad, por supuesto, y seguimos avanzando en eso, aunque no lo crean, seguimos avanzando. Primero que todo, obviamente, saludar a las autoridades regionales, quienes han sido un tremendo apoyo en el desarrollo de este proyecto, a la universidad, obviamente, al CIBA y todos los representantes, al Atacama Vaccine Laboratory, sus representantes, por supuesto, al Instituto Milenio, que sin ellos, la verdad es que no podríamos haber tenido este enlace con las universidades del sur de Chile, a los alumnos, que ustedes obviamente están acá para seguir el trabajo que después dejen todas estas distintas personas que han empujado este carro, y a los invitados internacionales y nacionales que están acá presentes. Ustedes se preguntarán por qué está un diputado hablando acá, o sea, ¿qué tiene que ver con la ciencia? La verdad es que si no empujamos todos los antofagastinos, si no empujamos todo este tipo de proyectos, Santiago y el resto del mundo no nos conoce.
La gracia de Antofagasta no está solamente en el mirar al cerro y mirar todo lo que es el cobre, el litio, tampoco está en el mar con toda su maravilla, por supuesto que lo hay, pero no es solamente eso, no es solamente mirar al cielo y ver grandes telescopios. La principal riqueza son ustedes, son los estudiantes, son los profesores, son las personas que vivimos acá. Y en ese sentido, Antofagasta, estoy seguro, y así lo fue el año pasado cuando empezamos a hablar de vacunas a través del Instituto Milenio, a través de la universidad, pasó a ser uno de los centros del país en términos de hablar de vacunas. Eso que nos salvó, eso que nos puso en el top 5 a nivel internacional de vacunación, bueno, eso fue también gracias a las personas que están acá. Esa es la importancia que tiene, esa es la gran importancia que tiene avanzar en esta clase de proyectos. Les quiero decir también que eso fue un imán en cuanto a los privados. Tuvimos acá a una empresa china que es Sinovac, que fue la que trajo Coronavac, no sé si se acuerdan, la que probablemente todos se pusieron al principio, y ellos siguen interesados en poder tener un desarrollo acá de una planta, y eso ligado a la universidad, y esperamos que terminada la planta de Santiago puedan seguir trabajando. Muchos me han dicho, oye, eso no se va a llevar a cabo, se ha quedado un poco dormido. Seguimos trabajando como hormiguitas día a día para que se vuelva presente y podamos decir que Antofagasta es el polo de la ciencia y la tecnología. Así de simple. El polo en términos energéticos. Yo soy presidente del Grupo Interparlamentario Chileno-Japonés. Lo único que quieren los japoneses es venir a hablar de hidrógeno verde. Los chinos, los alemanes, todos ellos quieren hacerse presentes en nuestra zona, pero necesitamos ¿qué? Necesitamos de ustedes, de la capacidad de ustedes para poder hacer esos lazos, para poder traer a esa gente y decirle, sí, hay capital de trabajo acá, hay personas capacitadas. Para ir terminando. Israel, y es importante lo que decían los representantes los representantes del gobierno regional. Mire, Israel, para darle un ejemplo, aproximadamente invierte un 6% de su PIB en investigación y desarrollo, en desarrollo, en poner plata en cosas que van a generar más dinero, que van a generar mejor calidad de vida. Chile invierte un 0,38. Eso es lo que invierte Chile hoy día. O sea, esa es la diferencia de un país que es prácticamente muy parecido al de nosotros, tiene desierto, no tiene agua, y poniendo esa cantidad de plata, hoy en día son líderes en muchos temas. Hacia allá hay que ir. Yo alabo las palabras del representante del gobernador. Sé que van a seguir en esa línea y tienen absolutamente todo mi apoyo. Pero no es solamente dinero. Aquí están las personas, aquí está la gente, lo que les decía, sus capacidades. Sin duda, con ello vamos a poder empujar estos grandes carros. Tienen grandes ejemplos, la doctora Margarita Lai, los profesores, el vicerrector, el doctor Calergis, que prácticamente es un antofagastino más que viene acá a participar, y yo creo que hay que seguirlos a ellos porque es plata, es cierto, pero aparte de eso también es mucho trabajo, es mucho sacarse la mugre para hacerse valer y hacer Antofagasta un polo y un centro de investigación. Muchas gracias.
Agradecemos las palabras del señor diputado. A continuación, invitamos a las y los presentes a un recorrido guiado por el Laboratorio Clínico Molecular y también por el ADVALAB. Van así a ser guiados por los investigadores del laboratorio, posteriormente a un coffee break, y nos juntamos a las 11:15 para comenzar con el Simposio de Inmunología en primavera en el desierto de Atacama, desde la Edad Media, de COVID-19 al Renacimiento por la vacunación. Les recordamos a las 11:15 nos volvemos a juntar aquí, y además les recordamos que algunas de las charlas son en idioma inglés, y para poder acceder a la traducción simultánea deberán escanear un código QR que se encuentra en el ingreso a este salón. Muchas gracias. Muy buenas tardes a todos y a todas. Invitamos a las personas que estén fuera del salón para que se incorporen a la audiencia para poder dar inicio al Simposio de Inmunología en Primavera en el Desierto de Atacama, desde la Edad Media de COVID-19 al Renacimiento por la vacunación. Les recordamos también que algunas de las charlas que se van a dar, que se van a realizar en este salón están en idioma inglés, para lo cual se ha implementado un sistema de traducción simultánea, al cual pueden acceder haciendo clic en el código QR que vemos acá y el código. Eso también se lo recordamos a las personas que nos están viendo por YouTube Live, para que también hagan clic en este código y puedan acceder a la traducción simultánea. Hecho este recordatorio, damos inicio entonces a el simposio con la charla Vacunas conjugadas y bacterias encapsuladas, éxitos y desafío, que está a cargo del doctor David Goldblatt, profesor de vacunas e inmunología del Departamento de Infección, Inmunidad e Inflamación de la University College of London y del GOS Institute of Child Health del Reino Unido. Invitamos al doctor Goldblatt a acercarse al estrado.
Speak loud. Okay. Okay, pointer doesn't work. Well, thank you very much for inviting me today. It's a great pleasure to be here and to speak to you about bacterial vaccines. Could I have the first slide, please? No, that's not my presentation. I can talk about this, but it's not my presentation. Ah, that's better. This is my presentation. So I'm going to talk about conjugate vaccines, which are vaccines that have been designed to be made to protect us against bacteria. And there are many bacteria. It would also help me if the pointer worked. Ah, okay. 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 Perfetto. Right, so there are many bacteria that cause problems for humans, and you see some of them on this slide. And the reason these are all on the same slide is because they all have around the bacteria a capsule which is made of sugar. And that sugar capsule is a difficult one to make into a vaccine. And so conjugate vaccines have produced solutions for some of these pathogens that you see on the slide. And there are many others where there's a lot of work going on to develop conjugate vaccines. The one that I'm going to talk about today is the pneumococcus, because that causes a lot of pneumonia, meningitis, sepsis, and infections in the ear in humans, and causes a big burden of disease. And therefore, I'm going to describe to you the experience with conjugate vaccines for preventing pneumococcal infection. And I'm going to talk to you about the successes that we've had, and then I'm going to show you how we have some new challenges which we are now facing with some new vaccines as solutions. So the outline of the talk, first I'm going to tell you a little bit about the biology of these bacteria. Then I'm going to tell you about conjugate vaccine development and the impact of those vaccines. Then I'm going to show you how new pneumococcal serotypes have replaced the ones that we're protecting ourselves from with vaccines, and tell you a little bit about 2 new ones that were licensed in the last 2 years. I'm then going to tell you a little bit about some of the work we've done on giving infants fewer vaccines, but with the same impact, and then just next steps in this field after COVID. So the capsule is very important. This is the capsule that I'm drawing here on the outside of the organism. It's very important because it is the molecule that we use to identify different serotypes of the pneumococcus. And there's now more than 100 serotypes described. But the capsule is also very important as a virulence factor, because what it does is it prevents complement binding to the bacteria. And as many of you know, if a complement binds to bacteria, it can kill the bacteria. However, it's also a target for antibody. So if you have antibodies binding to the bacteria, then the reason that you can get protection is because the antibodies have a receptor on their surface for complement. And when complement binds to antibody, you can then get cells that come in and bind to the FC receptor of antibody and complement, and this phagocytic cell kills the bacteria. So this is the way that you protect somebody against the pneumococcus. And this is a slide that shows you the age of individuals on the x-axis. And then in the years before we had any conjugate vaccines in the UK, the number of cases or the rate per 100,000 of diseases. So these are all children under 1 year of age. You can see very, very high rates of disease, pneumonia, meningitis, and things like that. And then here, where most of us are, you get protection from natural immunity. And then when you get older, that's when you get another problem with the pneumococcus. So there have, of course, been vaccines that have tried to prevent particularly this disease, and they have been based on the capsule of the bacteria. And as I mentioned before, the capsule is a very limited vaccine, but the very first vaccines for pneumococcus were made just from the capsule and actually were tried in miners in South Africa, because when they went down the gold mine, they got a lot of pneumonia, and they tried that 100 years ago for the first time. So the problem with these polysaccharides as vaccines is they are able to induce antibodies, but because they bind, they're very big molecules and they bind to B cells, they cross-link immunoglobulin, and you do get some antibody, but it's a very limited response, partly because there's no T cells involved. So you need T cells to help B cells make antibody. And because there's no T cells, you get a very poor response below the age of 2. So these polysaccharide vaccines can't prevent disease in children. The other thing is that there's no B cell memory induced when you just have B cells with no T cells. So those are two limitations of polysaccharide vaccines that have been overcome by the development of conjugate vaccines. And this is what a conjugate vaccine is. You take the sugar and you put it onto a protein and you chemically conjugate it. And this completely transforms the nature of the interaction with the immune system. Now, this technology, this improvement was known about in the 1930s already, but it was only in the late 1980s that the very first vaccine that was using this technology was licensed for humans, and that was the vaccine for Haemophilus influenza B. So the way that the conjugate vaccines work from an immunological point of view is that you still get the B cell recognizing the sugar antigen, which is the capsule of the pneumococcus. But B cells, not many people focus on this, but B cells are very good antigen presenting cells. And when the B cell sees this polysaccharide antigen, but it's chemically linked to the protein, the B cell will take up the protein and present the protein in the context of class 2 to a CD4 cell. And that leads to some cytokines. And then basically what happens is you get affinity matured and isotype switched antibody, which is able to be induced even in young babies at birth. And that leads to plasma cells, which live in the bone marrow and live for a long time and provide protection. But most importantly, it also leads to memory B cells, which probably for the pneumococcus are important here in the nasopharynx, which is where the pneumococcus likes to live. So the very first pneumococcal vaccine, conjugate vaccine that was licensed in the year 2000 after a very big efficacy trial with 80,000 babies. And it was a vaccine that contained 7 serotypes. So these are all combination vaccines, and it was the 7 most important serotypes at the time. And I'm not going to go through all the details, but in every country in the world that introduced this vaccine, there was a very, very important decline in meningitis and sepsis, pneumonia, ear disease. And importantly, it was also able to stop the pneumococcus coming into the nose. Now, I'm going to show you why that's so important. So many of you will recognize this. There's a new baby over here. There's a toddler, maybe 2 years old, and the grandparents come to visit. Now you can see his face is very red. And if you are doctors in the audience, you know that people who drink a lot of alcohol have a very red face. So just remember that. He drinks a lot of alcohol and he's not very healthy. He comes and the toddler has lots of pneumococci in the nasopharynx, and then they come to visit the new baby, and then the pneumococci spread to the grandparents, and then sadly, because the pneumococcus does this, it's a very important pathogen in old people. So the grandfather dies when he comes to visit his little grandchild. So what does the vaccine do? Well, when you give the vaccine to the toddler, what happens is it reduces and prevents the acquisition of new pneumococci in the nasopharynx. And what that does is that prevents the pneumococci from going to the parents and to the younger baby. And this is called the indirect effect. So I'm going to show you how, by immunizing babies all over the world, we've reduced the amount of disease in adults as well. So this is the impact of these vaccines. So this is what I showed you before in England and Wales, in the period before we introduced pneumococcal conjugate vaccines. So we introduced the pneumococcal conjugate vaccine in 2006, and the rate of disease under the age of 1 was 35 per 100,000 for invasive disease. And then about 4 years after introduction, we introduced 2 doses in the first year of life and a booster at the age of a year, just the same as in Chile. And that fell after 4 years to 0.32 per 100,000. So it almost got rid of the disease due to those 7 serotypes. Now, this dose here prevents the spread to the adults. So if you look at the over 65s over that period, the amount of infection went from 17.7 per 100,000 down to 0.55 per 100,000. So a very, very important effect. Of course, there's many, many more people over 65 than there are under 1. That's only 750,000 people. There are many millions over 65. So this is a very, very important impact of these vaccines, and this is called the indirect effect or the herd effect. So the 7-valent vaccine was licensed in 2000, but as I said, there's more than 100 pneumococcal serotypes now. So the companies worked on developing first a 10-valent vaccine, and then in 2010, Pfizer licensed a 13-valent vaccine. So these are 2 vaccines that were licensed after PCV7 because we knew that we would get more diseases. And so here is the experience in the United Kingdom. This is the PCV7 serotypes, and you can see when you introduce the vaccine, they go away. And the green ones are the serotypes that are caused by the serotypes in PCV13, but not in 7. And so we introduced PCV13 in 2010, and you can see here PCV7 and 13 serotypes are well controlled. But you can see we've had a little increase here. This is the situation in Chile, which was published last year in a big study, which is many Latin American countries have the surveillance, which they do together in the system called Cereva. And here you can see PCV10 was introduced in Chile in 2011, and you can see all the cases, they go down quite quickly. Now, Chile introduced PCV10, and these 2 serotypes, these 3 serotypes here are in PCV13 and not in PCV10. And you can see that there's quite a large, about 30% of the serotypes causing disease in 2017 are 19A, 3, and 6A. And so in 2017, Chile made a decision to introduce PCV13. And that's what's used in Chile at the moment at age of 2 months, 4 months, and 12 months of age. Now, this is the impact in the adults that I was telling you about. Here is the reduction in disease due to the 7 serotypes after the introduction only in the children, no vaccine in the adults. And then here's the increase of PCV13. And then that's what happens when you introduce PCV13. And this is, I've stopped here because the pandemic interferes, as I'll show you in a moment. So here you can see an increase in non-vaccine types, and therefore an increase in all cases. And I'm going to talk a little bit about how we deal with that in a moment. So the serotypes that are causing this disease in the mainly over 65s are, you can see here, these serotypes, and I've illustrated them here, 8, 12F, 9N, 15A. And so the companies knew that they needed new vaccines and they would have to have these serotypes in them. And so in 2021, Merck licensed right in the middle of the pandemic a new vaccine with 15 serotypes. And then in the same year, Pfizer licensed a new vaccine which contains all of these serotypes, plus these 2, plus these, to give you 20 valents. So now we have this vaccine licensed for adults and this vaccine licensed for children and adults. And I'm going to say a little bit now about the amount of disease left that is included in these serotypes and what we might be able to do to protect children from and adults from these new serotypes with these vaccines. So the questions are at the moment, what proportion of pneumococcal invasive disease is due to the additional serotypes in either of the two vaccines? And should these two new vaccines be introduced for children? PCV15 is licensed, but not 20 yet, and adults. And I'll take you through some scenarios. So the first thing to point out is that the amount of disease between the children and adults is very different. This is data from 10 different countries in Europe. And what you can see here is that the rates of disease are 3 times higher in the adults than in the children. So when I talk to you about amount of serotypes causing disease, I'll give you the proportions, but for children, it's about 3 times lower than for the adults. So here's the data for children from that network. These are children under 5. And this is the last year before the pandemic proper. And this is telling you the proportion of serotypes that are in the different vaccines. I'll make it easy for you. That's PCV13, 15. So the first thing to say is that PCV13 hasn't got rid of all the disease. There's still a little bit of residual disease. And this is the percentage of increase in coverage from these two new vaccines. If you use PCV15 in Europe, you get an extra 25% coverage. And if you use PC20, you get an extra 64%. And so these are the numbers that the governments and the committees are going to have to think about when they try and work out if it's important to introduce this vaccine in children. And if you look in the US, it's very similar as well. This is before the pandemic. PCV13, about 21% of invasive disease is still caused by the serotypes in PCV13. PCV15 adds 17%, and PCV20 takes you up to 60%. So we'll have to work out if it's cost effective to introduce this for children. Now in adults, it's a little bit different. It's the same. This is the network in adults, and those are the vaccines available, and that is the additional coverage. So now remember, the rates are about 30 per 100,000, and so potentially with PCV20, you might be able to prevent almost 70% of infection. So that's something to think about as we decide what next to do. And then this is data from the US showing you that PCV13 was actually introduced for all adults in 2014. That's the increase in coverage. But what I want to show you is that PCV13 made no difference to the disease in adults. So the US was the only country in the world almost to introduce PCV13 for adults, but it made no real difference. So they changed their recommendations in 2019. So here are the options. We need policy decisions about these. So for children, we need to decide what to do. Should we immediately replace in Chile PCV13 with PCV15, which is licensed for children, or should we wait for PCV20? So the Chilean government committees are going to have to make that decision based on how much disease there is. Then for adults, many countries, including the UK and Chile, have a policy where individuals over 65 years of age get this 23-valent polysaccharide vaccine. It's probably not so good at preventing pneumonia, and so we're going to have to think if we should replace 23-valent with one of these two vaccines. Or we wait for them to be incorporated into the infant program. And as I showed you, when you introduce vaccines into the children, you reduce the disease in the adults. And so we're going to have to wait. It's obviously much cheaper to introduce PCV20 in children and to watch the indirect effect than it is to give millions of adults in Chile 20-valent vaccine, which is going to be much more expensive than PPV23. So the last thing I want to talk about is just the numbers of doses of vaccines we give young babies. So you can see that we got good control of PCV disease in the UK. And so we wondered if it's really necessary to give 2 doses. And so we did a trial wondering if we could just give 1 dose and 1 dose. And what that does is that saves money for the government, but also gives you space to introduce new vaccines. Perhaps if we have RSV or even if we have to give COVID vaccine, we have more space to give the babies vaccines. So we did a trial where what we did is we randomized 2 groups of children to get vaccine, PCV13, at either 2, 4, 12. That's how you do it in Chile, or just 3, 12. Now, the nice thing about the pneumococcus is we have a correlate of protection of 0.35. So you're able to look at the proportions of infants who have antibodies over 0.35 after the 12-month dose. And you can see basically it's completely the same between the two. And so I presented this data to our committee on vaccines, and they made a decision that they would change the policy, and from the first quarter of 2020, we would have a 1+1, which is what we call this, 3 months, 12 months for all babies in the country. So here's the impact of that change. This is July to June for 2016-17. This is the winter, when you get more invasive pneumococcal disease in the country. 2017-18, 2018-19, and then we introduced the policy change here. And you see pneumococcus goes away, and then the red line, it doesn't come back up in 2020-21. So we think maybe, is this the vaccine? Sadly, that's not the vaccine. It's, of course, the coronavirus pandemic. So everybody is locked down, has to stay at home. So one of the things that's happened here and in many countries in the world is that there's been very little pneumococcus disease. In the same way, there was very little influenza, very little RSV. And if you look in the data in Chile from the Institute for Public Health Institute, you see here, 2020, many, many fewer isolates of the pneumococcus. So we're not quite sure if 1+1 is going to work. And in fact, we've now seen that there's a little bit of increased disease now that we start coming out of the pandemic. This is July to June, as I showed you before, for the adults over 15. This is 21-22, no change. But for the children under 15, there's more disease in 21-22 than there was before the pandemic. And you can see it's mainly the ones that are 1 to 4 years old. So maybe what happened during the pandemic is we weren't getting children to see the pneumococcus, and so their natural immunity started declining, and therefore they weren't boosted, and therefore they got infection. So we're all watching very carefully to see what happens after COVID, to see if we get a rebound with other infections. So in summary, the next steps for the use of PCVs. Firstly, they've been very, very successful in reducing the burden of disease due to the serotypes in the vaccine. The replacement serotypes with these new ones has eroded that benefit, especially in adults. But we need this good quality surveillance for pneumococcal disease to be able to know what's coming up and what we should do with the new PCVs. These two vaccines have been licensed on immunogenicity. There were no efficacy trials, so we'll need surveillance to work out once we introduce them if they work or not. And we can also want to make bigger combinations. There are several being developed now. I'm working on this one, 25 valent. But ultimately, what we'd like is a universal vaccine which contains proteins that doesn't rely on serotypes changing. But at the moment, the most important aspect of controlling pneumococcal disease is to ensure that children are immunized according to the national guidelines, and thus maintaining high coverage for existing recommended PCVs. And all of us in all the countries that we come from will be struggling for the next few years to work out what we should do with PCV 15 and PCV 20 if our governments can afford it. So just to thank the members of my lab who do a lot of the work that I showed you, and the UK Health Security Agency that I work very closely with, who monitor the disease in the country. Thank you very much.
Sí.
Questions? Oh, okay, yeah, sure. Yeah, sure. Sorry.
¿Cómo están? Buenos días, buenas tardes. ¿Cómo están todos? Gracias por estar aquí. Y bueno, después de esta excelente charla de nuestro invitado, queríamos saber si tienen algunas preguntas para él. Así que ahora es el momento. Si quieren lo pueden decir en español y yo les hago la traducción. Yes, Dr. Leonard? Yes.
What kind of current protein is used normally in this type of vaccine? There are some different current protein. No, the carrier protein for this is CRIM.
Oh, doctor, please say.
The carrier protein for the Pfizer vaccine is CRIM. And the carrier protein for Merck is also, if I remember correctly, CRIM, but I think there are one or two that may be on tetanus, because not all the serotypes work so well with CRIM. CRIM is a cross-reactive mutant of theriotoxin. That's the main one.
Thank you. Dr. Gonzalez?
I'm not sure if you can expand a bit on the second conclusion on how the vaccination in the infants has eroded the immunity of the adults. If I understood well from where I saw your data, the strains that are not contained within vaccine, it seems that they affect mainly the adults and not the infants.
Yeah.
Why aren't the infants also still?
Okay, that's a very good question. Do you want to translate into Spanish? It's being translated.
Yes,
Okay.
yes.
Well, that's a very good question. So what happens is if you make space in the nasopharynx by getting rid of the original serotypes, the new serotypes come in. And because they come into the nasopharynx, they spread to the adults. And so that's what we call replacement disease. And as you've noticed, they cause more disease in the adults than they do in the young children. So not all serotypes are equal when it comes to their pathogenicity. So it would appear that particularly in those over 65, where we see most of the increase, there may well be a certain susceptibility to some of those serotypes because of other factors, which we don't understand fully. And the children remain relatively resistant to infections with those particular serotypes. But that is something that has been noticed and remains a puzzle as to exactly what is the biology underlying that. Yeah, there's a question.
Question? Yeah, the student.
The student, yes.
Student Vicente. Vicente.
You'll have to interpret
Yes.
for me.
Yes, yes.
Okay.
Vicente, lento por favor, para traducir.
Probando. 1, 2, 3. Bien. Sí, pero tienes que acercarte un poco acá para poder... Estamos improvisando.
Better be good.
Ahora sí. ¿Se escucha? Hola, me llamó mucho la atención el punto de la vacuna universal que mencionó en su presentación.
Okay. He got pay attention to him, the universal vaccine based on conserved
Proteins.
regions of
Proteins, yeah.
Yes.
Sí, entonces como estudiante me preguntaba cuál sería el primer paso para poder crear una vacuna universal.
What will be the first step to create this kind of
Okay.
vaccine?
So for the last 50 years, people have been working on these. And you know what happens usually is they work on mice and they find a protein that works beautifully on mice. It protects the mice against meningitis and pneumonia. And they come to the human phase 1 trials and the early phase 2, and it has no impact in humans at all. So one of the problems in the pneumococcal field is that the pneumococcus is not a natural pathogen in the mouse. So you have to find the right mouse strain. You have to find a little pneumococcus that's a little bit different to everybody else. And then you get beautiful protection in the mice. But unfortunately, that doesn't translate into humans. So as I say, for 50 years, people have tried either one protein or combinations of protein, and they don't seem to work. And there's two potential issues. The first is that because there's a capsule in the pneumococcus, some of the proteins are covered during the pathogenesis of infection, and the human immune system might not have access to the proteins because it's covered in a capsule, like a shield on the outside. That's one thing. The other thing is that pneumococci are very good at changing the level of expression of proteins. And so they can upregulate proteins and downregulate proteins, and they may well also therefore be able to escape, because many of the proteins that are being targeted are not absolutely essential to the pneumococcus surviving. So it becomes a problem, and the best way forward is to have a combination where you have the sugar and the protein carrier from the pneumococcus. But even that so far hasn't worked. So people are still trying to find this universal protein. And it's proving very, very difficult.
¿Necesita traducción? ¿Necesita traducción? ¿Quiere traducción? ¿Sí? ¿O tienen interpretación? ¿Lo entendió? Bien. Gracias. Thank you. Dr. Carreño, please.
Thank you, David, for the presentation. So,
Hold on, please.
Okay.
Thank you very much, David. It's related to what Pablo just asked. So I was thinking,
because they are toddlers that actually, gave the disease to elder people, right? So, but they were vaccinated before.
Yes.
From a different vaccine. So when they change the policy, do you think it's a good idea to give them a boost to toddlers, like another dose, but
ones who
with
didn't, yeah,
with
okay.
the updated vaccine?
I'll come back also to Pablo's question, because when you see the slides, it's also a matter of the scale. The reason there's so much more disease in the adults is because there's so many more adults. There is still a little bit of increase to those new serotypes in the children, but not as much as the adults, which is why there is this imbalance. So when we decide to change the vaccine, it's particularly in the UK, we have to think very carefully, because at the moment what we give is we give 1 + 1. So if we produced, let's say today we wanted to start PCV15, the little babies have only had one dose of PCV13. So we don't know that 1 dose of PCV15 will be enough. So that's the first problem. And then if we don't give it to the 1-year-olds, let's say they've had their PCV13 already and they don't get the new one, we're going to have lots of young children who are going to be able to pass the serotypes to their parents and grandparents for many years. So the best way to probably do that is to do a catch-up campaign where you decide that in 12 months you immunize everybody in the country under the age of 2 or 3 or 4. So that's probably, we're having these discussions on our committees at the moment. That's probably what we're going to do, a limited catch-up, and then start the program in the children. Our problem is there's no data in the world on 1 + 1. The PCV15, which is licensed for children, there's some data on 2 + 1. So what we may have to do is either very quickly do a study in my lab on 1 + 1 for the new ones, or start with 2 + 1 for maybe a year and then change back to 1 + 1 when we have the data. So the catch-up is the most important.
Thanks.
But it's expensive.
Yeah. I guess.
Thank you.
Yes.
Any other?
I have another question. So, it's any other question for the public? Or?
In the back, ¿hay alguna pregunta?
Sí, para dar la oportunidad a los estudiantes. Okay. Thank you very much, David, for your talk and for coming here. We really appreciate having you here in Chile, in Antofagasta. So my question is regarding the combined vaccines that you mentioned in the introduction of your talk about several pathogens that have this capsule that is part of the pathogenicity mechanisms of several bacteria. So regarding the production of optimization of vaccine application to people, it is possible, in what is the experience, because I don't know very much about that combine polysaccharide vaccines that include several bacteria to prevent infectious diseases.
Yes. Well, there's no barrier to that. The only problem is that we have slightly different strategies. So, for instance, for meningococcal C conjugate vaccine, we now only give it in the 2nd year of life. Pneumococcus, we give 1 dose and 1 dose. And Haemophilus influenza B is mixed in with acellular pertussis, diphtheria, tetanus, inactivated polio, hepatitis B. So it's a big combination vaccine. And there you get that 3 times.
Right.
So in order to do what you're suggesting, which is a good idea, you'd have to take Haemophilus B out of the big combinations. You'd have to take and give more men C more often, which you don't really need to. And you would have to optimize 1 + 1 for all of them. So I think it would be quite difficult. But in theory, you're absolutely right. We could have a meningitis vaccine. That could be a combination of all of these.
Right.
The ones in development, typhoid has recently been licensed, typhoid conjugate, and the ones that are coming up are group B strep, but that would be for pregnant women to try and prevent the very early infections in their babies in the first month of life. So we wouldn't be using that for babies. And then, as you know, we're working on a Klebsiella conjugate vaccine. Right. That would probably in the beginning be for older people maybe coming into hospital so that we prevent nosocomial infection. But you're right. Those could all be a nice meningitis combination for the future.
Okay. Thank you.
Thank you.
Muchas gracias. Muchas gracias.
Bien. A continuación, la doctora Alba Grifoni realizará la exposición Monkeypox, definición de objetivos de antígenos para disectar el virus de las vacunas VACV y el virus de la viruela del mono MPXV, respuestas específicas de las células T en humanos. La doctora Alba Grifoni es instructora e investigadora del Center for Infectious Disease and Vaccines Research de la Joya Institute for Immunology en San Diego, California. Invitamos a la doctora Grifoni a acercarse al estrado. Les recordamos que al final de la exposición de la doctora se abrirá el espacio a preguntas para que las preparen. Muy bien.
Gracias. ¿Tiene que hablar? Sí. Hello. So I would like to start by thanking you for giving me the opportunity to be here. I work and I've been working in viral infectious diseases for the longest time. In the past 2 years, I've devoted my efforts in COVID-19. But in reality, one thing that I found extremely important is the concept that we need to start to be better prepared to emergent viral infection. And for that specific reason, today, instead of talking about the COVID work, I would like to spend time to talk about Mpox. And for the ones that are not aware, I'm referring to the monkeypox virus. And just 2 days ago, the WHO is changing the nomenclature to actually avoid any stigmas about this disease. So throughout my talk, I'm going to talk about Mpox, referring to the disease, and MPXV, referring to the virus that caused this disease. And so why Mpox is becoming important? So Mpox virus, differently from COVID-19, is not a new virus. In reality, this virus has been circulating since the 80s and has been spreading particularly in endemic areas. The reason why we're starting to raise awareness about it is because this virus now is going away from endemic countries. And in particular, there has been an outbreak that caused over 80,000 cases throughout different populations worldwide, which kind of suggests the fact that, and that's something that we should remember about infection in general, small outbreaks can easily blow up in bigger outbreaks and potentially pandemics. And so the more we start looking into these small outbreaks, the more we start to study about them, the earlier we can actually act against those. And so that's incredibly important in my opinion. And so just to give you an idea about the current case profile of the Mpox infection that has happened, I would like to direct the attention that there has been a prevalence in the type of people that have been actually exposed to the infection, particularly men who have sex with men, and the virus has been transmitted particularly through sexual transmission. However, this virus can be transmitted just by contact to contact. And so in this case, unfortunately, this particular population has been hidden, but that doesn't mean necessarily that in the future, this virus can spread to different type of communities. So that's something very important to take in mind. Another point is the fact that in these specific outbreaks, there was a lot of people living with HIV. And so that's another point that we need to start be aware of, that each individual can be exposed to multiple infections at the same time. And we need also to be mindful in trying to understand how the different infection can play a role in the way our immune system behaves to that. So a little bit about the symptomatology. And so there are a wide range of symptomatology that you can have with Mpox. In these specific outbreaks, the majority was rash. And the fact that there is a component in sexual transmission, many of these rash were actually in the genital area, which suggests a lot of pain. One point is that in the context of children, this type of disease can actually be lethal. And so once again, the variety of lethality and severity that you can have about disease really change depending on the target population affected. So a little bit more about orthopox virus in general. So as I mentioned to you, mpox is not a novel virus, and in reality, we have been studying in general the family of orthopox virus in the past years. And so when we think about orthopox virus that belongs to the poxvirus family, in reality, there are different type of viruses that we have been studying throughout the years. So the first one that is actually the most famous, perhaps, is the smallpox. And so many of you might recall that smallpox has been a huge burden on the worldwide population, and we were able to actually eradicate that through vaccination. And I'm gonna go into that point a little bit longer later. Another point is in terms of vaccine strategy, what has been done in the past and has been successful in many cases is to use a virus belonging to a different species that are close enough to essentially induce an immune response that can protect against the disease. And so for that reason, for instance, in the context of the vaccinia virus, has been used in the context of vaccination to fight against smallpox, and very recently has shown to have a protection effect also in the case of mpox. So what is the challenge with this virus when compared to different viruses? The orthopox virus are huge. They are composed by over 200 different proteins. And so just to give you a difference respect to SARS-CoV-2, SARS-CoV-2 has only 25 different proteins. So we are increasing the complexity of over 10 different folds. And so that is the reason why when we start studying how our immune response react to that, the fact that this virus is so big is actually creating novel challenges, both in the context of understanding vaccination and in the context to understand which type of immune response is protective and against what type of antigen. As I was mentioning before, in the context of smallpox, vaccination has been incredibly successful. We were able to eradicate smallpox in the 1980 and 1972, actually in the United States. And that was possible because this specific virus has no animal reservoir. What does it mean? That essentially it was hitting only the human population. And so the moment in which you vaccinate the human population, there was no way for the virus to actually hide in other species. That is not the case for other orthopox viruses, which is the reason why we need to be mindful and think maybe once again to a vaccine strategy against different orthopox viruses. And so a little bit of history about the vaccines that have been used in the context of orthopox. As I mentioned to you, vaccinia virus has been the strain used for this vaccination. However, the way the vaccine has evolved throughout the time really depends actually on the needs for this vaccination. And so when we design a vaccine, there is always a balance we need to take into account. One is immunogenicity and the other one is safety. When we encounter a viral infection that is actually incredibly dangerous, sometimes we prefer to have a vaccine that works very well, although maybe the safety is not as good. But the more you get rid of the pathogen that is actually really dangerous, then safety is a very important factor. So in the context of smallpox, considering how burden was these diseases, the first type of vaccine that was used, the Dryvax, there was a combination of these different strains, was actually used to try to eradicate the disease. But one point is that this type of vaccine in immunocompromised people can create some severe consequence. So in the moment in which you eradicate this disease and you want to think about a vaccine that can protect to different other orthopox virus, consider that the burden is much less than what we have experienced in the past with smallpox. Safety become a very important concern. And so in the past years, there has been several efforts by the scientific community to try to improve the safety of the orthopox vaccine. And so the way they did that was first to isolate the combination of vaccinia strain to the ACAM 2000. And that was essentially trying to go for the least pathogenic strain among the different pool that was used at the time. But once again, this is a replicating virus, and that can cause issues in immunocompromised population. And so then finally, the MVA, which is the modifying vaccine Ankara, has been generated. This is once again a live vaccine, but does not replicate, so it's much more safe. One thing that happened throughout this process is that the fact that this virus does not replicate anymore is because it has lost several proteins. And finally, both ACAM 2000 and MVA are currently licensed against Mpox, and that is due to observational fact and due to experiments that have been performed in animal model. But we actually don't really know how these vaccines are working against Mpox. So a little bit about adaptive immunity, and I thank David because he gave you a little bit of background. So about the different components of the immune system, one that is very important in the context of vaccination is adaptive immunity. And the reason is because they have memory, which means they encounter the virus once, they remember it, and then they're able to act much faster. This memory is what you try to trigger when you design a vaccination. Instead of having the danger to encounter actually the live virus, you use the vaccine to mimic first encounter so that the immune system is able to respond to that much faster. And so, as I was mentioning, there are different actors. We have B cells that produce antibodies, and these antibodies are able either to prevent the infection, those that are the neutralizing one, or to prevent the spreading of the virus, and those are the non-neutralizing one that interact with the innate immunity. But once the virus infects the cells, then that's where T cells are important. And so there are two kinds of T cells. The first one are the killer T cells. Those really are able to recognize a cell is infected and kills it, so they avoid the virus be able to replicate and go to different cells. The other important type of T cells are the CD4 T cells. And so those were the ones that David was mentioned. Those type of cells are the ones that are able to help the immune response to really coordinate together and try to have a good immune response against the virus. The truth is that everything is complex, and in reality, all of the components that I just told you about, they work together. So when we think about understanding a vaccine, it's important to have in mind both components in order to have a vaccine that is able to trigger an holistic immune response. So what do we know about T cells specifically in the context of Mpox? So we know that antibodies are very important in prevent the infection, and that applies to any type of viral infection. However, they're not always capable to completely prevent the fact that you have the virus infecting the cells. So this is why you need T cells. There are really no data in terms of the nature and particularly the durability of our T-cell response. And this is important because, particularly for a virus that we don't know when it's going to be the next outbreak, should we vaccinate now? Should we wait? How are we going to think about a vaccine strategy potentially? Even less is known about how the current vaccine actually behave in the context of Mpox. And so, as I was mentioning before, one observational study show an 85% capability to protect from disease when we use Dryvax. Gynus, that is based on the MVA that I was mentioning before, we know that can prevent disease. We have animal studies, but we really need to work much more on what's happening. And then finally, because the Dryvax vaccine has been done during the smallpox infection, so we really know what's doing. The MVA didn't do that because the time this was designed, the smallpox infection was not there anymore. So the other question that is important to understand is how those actually behave. And finally, how do we measure T cells? And so, as I was telling you before, this virus is very big. 200 proteins is very hard to actually measure T cell response in this case. And that is because differently from antibodies that recognize surface protein of the virus, T cells can virtually recognize all the 200 proteins, and we don't really know which one are going to be the most important. So one approach that has been done experimentally so far is to in vitro infect the cells to actually understand how our T cell responds. But that has some challenging. The first is the fact that you need a higher safety lab to actually study that, and that limits the amount of laboratory that can actually check that. The second is considering this virus has a different time of replication, different proteins are going to be produced at different times. And so by doing that, we can bias the results we have about our T-cell response. So in order to try to overcome this issue, what we have been doing is to try to really develop an approach that looks directly at the proteins instead of infecting. And so how does T cells recognize actually the virus? They do not recognize the entire protein, but what they do is that the infected cells chop piece of this virus, and they present it in the context of the HLA molecules. And HLA molecules are very variable across the different human population, and this is the reason why T cells in general are much more stable across different variants of different viruses. And so what we were interested in understanding were the epitopes, so the portion of the virus that is presented and recognized by the T cell response. So because we know that MPXV and vaccinia, they belong to the same family, and we have done studies to understand how closely related they are, and we found that they are quite conserved, we decided to leverage the previous scientific information regarding vaccinia to try to understand potentially what are the most important proteins that are going to be able to tell us what we should look into in the context of Mpox. And so here, I'm just going to show you a tally. I'm not going to go too much into that, but essentially there was enough knowledge previously to be able to design pools with enough epitopes to actually be able to discriminate T-cell response. And so that's what we did. And when we look specifically at the portion we know T-cell recognized, we also were happy to see that other orthopox viruses and MPXV virus, they actually have very high conservancy. So our expectation is that thanks to these pools, we're able to measure vaccine-specific response, but they should also be good in measuring how we behave to monkeypox. So in order to test that, the first approach we did, because that was at the beginning of the outbreak, we didn't have still samples available, we went back to people that received the Dryvax vaccination. Those were a cohort of healthcare workers that were enrolled for a different studies at the beginning of 2000. And at the time, I just want to emphasize that the healthcare workers were actually having the Dryvax vaccination because many people were working on this in the labs to be protected. And so I'm going to show you the results that we found in the context before of CD4 cells and then CD8 cells. So one point I would like to emphasize, this T cells can essentially respond to a virus in two different ways. The first one is just recognizing and get activated. That tells you that the T cells is going to do something about it, whether producing cytokine or actually having a talk-to-talk with different cells. The other point is you also want to know effector, what the T cells produce. And so we developed an assay that allows us these small blood volume samples to actually be able to look at both contemporary. So this is the results. I'm showing you that in terms of magnitude, so how strong your response is, and in terms of frequency of response, because that gives you a different information, so how good is the vaccination in the general population. Essentially saying how many respond and how many don't. So when we look at pre-vaccinated individual, you will see that 50% of those has a response. And that was expected because we know these people receive sometimes in the past the vaccine. That is also good news because it suggests that perhaps the immunity that is induced after vaccination is actually long-lasting, although we don't know exactly how long. Once we see a 2 weeks post-vaccination response, we do see a significant increase in response, and then a slight wane, but it still remains stable at 6 months, and it's actually very similar to our pre-vaccination, which kind of suggests this is the point in which your immunity stops and then can last much longer. And that is kind of mirrored also in the context of the frequency of positivity. That is true if you look at activation, and even better if you look just at functionality. What about CD8 T cells? So the CD8 T cells have a different profile. And so essentially what we realize is that perhaps the longevity of the response for CD8 T cells is not as stable as the CD4 one. And in fact, we do see no previous response or a little bit of that, a good peak of response right after vaccination, but then it wanes again. And so that may suggest that perhaps in the context of orthopox virus, CD4 T cells may play a more relevant role than CD8. Finally, so far what I show you was just related to vaccinia virus, and so what we already know based on different studies. Then our question was, can we develop a new tool to study specifically MPOX particularly in people that get the infection. And so I'm not going to go too much into that because those are very complex bioinformatic analysis, but essentially we took the knowledge we had, we tried to get the equivalent for the monkeypox virus, and then essentially we tried to get the most immunodominant proteins, so the proteins that we know they're still recognized and exist in the context of monkeypox. And so essentially this is what we found. Although we have multiple proteins that actually contribute to the response, we were able to narrow down to a smaller list of proteins that actually account to the majority of the response. And so those are the ones that we actually use to perform T-cell prediction. At that point, the question was, if we go back to our vaccinated population, are they going to be able to recognize monkeypox? Essentially, the question was to mimic what can happen if I give a vaccinia virus vaccine and then the person get exposed to the infection. At the T-cell level, what you can see, whether you look at CD4 or CD8, is that the pattern is exactly the same. And so essentially, this suggests that T-cells are stable enough that even if they're given a vaccine with a type of virus, they're able to recognize the other one. And so that's good news. Finally, and that is more of a technical point, because CD4 are so stable and we see no CD8 T-cell response, we were wondering what is the quality of this CD4 response. And so one thing that I didn't mention before is CD8 T-cells are usually the one that kills the virus, and they do so by using granzyme B and perforin to actually cause lytic holes in the cells, and essentially that allows the cells to explode. What we found very interesting is that this portion of granzyme positive response is pretty high in the context of CD4 T cells. And so we know that sometimes in some infections, CD4 can also act as a cytotoxic T cells. In the context of this virus, it looks that they do it a little bit more than other viruses, and that can explain why maybe CD4 are enough. They're essentially doing the work of helper and cytotoxic cells together. So in conclusion, we were able to essentially find portions that are similar between vaccinia and MPX. And so that already put us in a good position to be able to essentially both understanding how vaccination works and also infection. We have a very stable response in the context of the CD4, and we also see that these CD4 are essentially polyfunctional. They're trying to do everything from helping to actually killing the infected cells. And so maybe that's a population we should focus more in the future. But we just scratched the surface, and there is so much more to do. We need to understand what happens if you get Mpox, what happens in infection, how does the acute infection works, what makes the difference between someone that has severe symptoms and does not, and particularly what is the difference across the different vaccination. Because this is going to really help us understanding what are going to be the future decisions we should take if this outbreak comes back again. And so another point that I would like to emphasize is that as a mission, what we have been doing during the pandemic was the capability to essentially allow labs all over the world to be able to measure a little bit easily T-cell response. So we create a hub for distribution in the context of SARS-CoV-2, and this is just an example in the context of the Omicron variant. And so we are planning to keep doing that for all the other viral infection we encounter, also in the context of Mpox. And we think that's important because the more you have science together working to the solution, the faster you get results. And yes, I just want to mention that this collaboration is not just all over, but also particularly in Chile. We have been having a great collaboration with Professor Bueno's lab in SARS-CoV-2, and we hope to expand it also to different viral infections so that also Chile can start studying much more T-cell response across different viruses. And so with that one, I would like to finish. I think science, as much as the immune system, is teamwork. And so the more we work together, the more we try to put together efforts to actually make a better work, the better and the faster we get to solution. So with that one, I would like to thank the people that have done this work, in particular my mentor Alessandro Sette and our collaborator in JCVI, and those have been done a lot of the conservation analysis that I mentioned but didn't really fully show today. With that, I take any question. Thank you.
Thank you very much. Muchas gracias. Y por favor, si tienen alguna pregunta, yo también se las puedo traducir. Para el doctor González, por favor.
So she guessed because I was on my way to lift my hand, and she said,
I read minds.
So thank you very much, Alba, for your talk. So I have a few questions. One of them is, so your data on the pre-vaccinated and then their response to mpox antigens relates very well with the clinical data that start to show up that those people who were previously vaccinated apparently had some levels of protection. So my question is whether you have been able to go like very look into the actual data of that clinical findings to be able to determine or not which is the importance of the T cell response, as you don't have yet the antibody response, or whether somebody with antibody response analysis has been able to relate your data and help determine the contribution of B cell and T cells in the protection.
Yeah, so that's an excellent question. For once, antibody response in this virus is actually more challenging than T cells. We have been trying to do several collaborations with different groups, and they really struggling in trying to set up a serology system that is able to address the question. So that's definitely something we're looking into that, and unfortunately I can't reply to the question yet, but hopefully soon.
And my other question was, I love the mega pools and the pools, but why not also go through the classical approach, which is grabbing whole virus? Although you'll be limited to the structural proteins, why not go to the whole virus and do the classical old school antigen presentation assays, where you just pull dendritic cells with a...
Right. So maybe I went very fast in that point. So one of the problems of this virus is that the kinetics of transcription of the different proteins is very different. You have early, intermediate, and late proteins. So depending how you set up this assay, you might have a prevalence of some proteins versus the other ones. In our case, our interest is to understand once you get the infection, so you get all the time possible for the virus to replicate, what are actually the responses that remain. So one of the limitations of doing the classical approach is that you're not going to be able to answer the question. You can have technical limitation to that. So that's the reason why we're trying this alternative approach. With that one, we're not suggesting you shouldn't do that, but perhaps to keep the two in parallel. That will be our suggestion.
Yeah, I was particularly mentioning the inactivated virus, like going for the structural proteins, right, straight away, not the other, which we know is the multifactorial.
So I can reply to that. In our lab in the past, they have been studying much more the response of T cells, particularly Alex has worked a lot in the pox virus, particularly after 9/11, there was a lot of interest because there was the risk to be used as threat pathogen. So what they found already is that the pattern of immunodominance of T cells is not necessarily related to the surface of the virus. So you might miss a lot of information by taking that approach.
Thank you.
Sure.
Muchas gracias, doctor González. ¿Alguien más de los estudiantes quieren hacer preguntas de este virus que está, digamos, circulando? Que es el virus de la viruela y ahora llamado mpox. Ahora es la oportunidad, tenemos una experta. Es la oportunidad. Pueden preguntar cosas relacionadas también. ¿Sí? Doctor Jorge Escobar, por favor. Un momento.
Gracias.
¿Español o inglés?
Okay.
50-50. She's Italian in todo caso.
Okay. My question is general, is very simple. Is a mpox pandemic possible?
That's a very good question. I am not sure we can answer to that, and I'll tell you why. There are a lot of components that actually can play a role in the spreading of a viral infection. And for instance, every time we try to make a list of what is going to be the potential threat of the next pandemic, we don't necessarily get the right virus, right? And so this is kind of like the mission that we have in studying different viruses, and particularly I'm interested in the underdog, the one that nobody is thinking about, because they can be the ones that if they really kick in a pandemic, we are going to have problems because we have no clue what to do about it. So I think this is the reason why we should study this. I don't know, and I cannot predict whether this can be a next pandemic, but do we really want to risk that?
Muchas gracias, doctor Escobar. ¿Alguna otra pregunta a la doctora Susan Bueno?
Thank you very much, Alba, for your presentation and also for the collaboration with Chile that has been very important for the COVID-19, and we expect to move forward with monkeypox as well and other diseases. My question is regarding just the specific points in the presentation, and maybe I didn't get how was the vaccination schedule for that you evaluated? Is just one dose or two doses separated by 28 days or 1 month? And this is the first question, and the other is about the CD8 positive T cells. I was wondering whether it could be maybe better to have 3 immunizations in order to get a more stable CD8 positive, but I think we still don't know whether this level of CD4 is enough for protection, or either we will need to have 3 vaccinations as the COVID-19, for instance.
Yeah, so that's a good question. So the vaccine that I show you in this data is actually the original one, Dryvax, and that has been recommended as a single dose. In the context of this study, what we did was essentially to enroll people getting a booster, because some got the Dryvax before, some didn't. In general, this is not recommended, actually. So I think this is a great point. I don't think anyone has been looking into that. But when we talk about number of doses, that said, Dryvax is 1 dose, but the MVA has been already envisioned as 2 doses, 28 days apart. So that might suggest that maybe with the attenuation, we might need to have multiple doses. At the best of my knowledge, nobody is trying 3 different doses, and that's probably something we should look into that. As of right now, the question is whether we look at one vaccine or the other one, are we starting to see a difference that can actually reduce immunogenicity? Because we know that the vaccine work beautifully in the context of smallpox, and the expectation is we'll do the same with mpox. So as of right now, Dryvax is kind of like the gold standard. So we just want to make sure that by attenuating this new virus, we're still reaching the same immunogenicity. Mm-hmm.
Sure. Muchas gracias, doctor Bueno. ¿Alguien más del público? Si no, yo voy a hacer una pregunta. I will ask a question. Alba, basically you showed that was a drop after the T cells response against this vaccine, Dryvax. And do you think it's because the virus maybe has mpox has a mechanism to somehow interfere with the immune adaptive response?
Yeah, thank you. That's a very good question. So I think one thing we don't really realize in the context of vaccine is not that when we gain a vaccine, you get a dose and then it remains as it is forever and ever. There is a natural moment of your immune response that is called the contracting phase, where after you get your response, you start reducing the amount of memory cells. And they are there and they're ready to expand again wherever you encounter that. So the fact that you see a decrease of 6 months, that doesn't mean necessarily that there is a mechanism that your T cells are not working. That type of curve, it is very similar to what we see in the context of other viral infection. For instance, in the context of COVID-19, we do have a good CD4 response. We do see a slight decline in terms of magnitude, but the frequency of responders remains pretty high. CD8, no, we see a decline as well. In other viruses, you may see a difference in kinetics. Maybe the waning goes a little bit slower. That, once again, doesn't tell you if your T cells are going to be there. An example that is successful is the yellow fever vaccination. We know that we need one dose, it goes for 10 years and more, and you still have T-cell response. They might be low in frequency, but as soon as they encounter the virus again, they react beautifully, and they're actually able to help you protecting. So I think magnitude and capability to actually protect us with T-cell response are two different components that needs to be studied.
Okay, thank you very much. Yeah. Well, thank you, Alba. Thank you very
Muy bien, agradecemos a la doctora Grifoni por su exposición. A continuación, realizaremos un break para el almuerzo y regresaremos entonces a las 15 horas a este mismo salón para continuar con el simposio. Bien, muchas gracias por haber asistido a la actividad de la mañana y los esperamos a todos y todas a la jornada de la tarde.
Pablo González. Bueno, el doctor Pablo González es profesor asociado de la Facultad de Ciencias Biológicas de la Universidad Católica de Chile. Él es experto también en el virus herpes virus y además es investigador asociado del Instituto Milenio en Inmunología e Inmunoterapia. Él también ha liderado, ha co-liderado sobre todo el estudio clínico de la vacuna CoronaVac, de Sinovac, en Chile, ¿ya? A través de todos los centros que hemos participado. Y, bueno, hoy día les va... Sí.
Ese título.
Ok. Les va a hablar sobre herpes simplex virus interference with immunity, focus on dendritic cells. Así que, bueno, un gran aplauso para el doctor Pablo González.
Muchas gracias, profesora Lai. Ya, entonces voy a cambiar a inglés por nuestros invitados. Cambié un poco el título, cambié el título de la presentación y el tema porque ya les había presentado, de hecho, a ellos hace apenas algunos días sobre COVID y sobre ese título que tenía, que era sobre diferenciar respuesta inmune humoral entre individuos vacunados, no vacunados y casos incidentes. Entonces voy a cambiar de tema a más lo que hacemos en mi laboratorio y voy a presentar en inglés entonces, por si quieren prender la traducción para que sea más fácil, más llevadera la presentación. So I'll shift to English for our invited speakers. So I just want to share with you some of the work we're doing at my lab regarding HSV and how this virus interferes with adaptive immunity, and mainly this through its interference with these immune cells that are key for mounting a T cell and B cell responses. So just the outline of my presentation is I want to show you and make you understand somehow why we are interested on dendritic cells and HSV, and then show you some new approaches that we're carrying out in my lab regarding the improvement of the DC outcome after HSV infection. So I'll show you data regarding an HSV mutant, data regarding the UPR unfolded protein response in HSV-infected dendritic cells, and briefly, very briefly, 2 slides, some lipid metabolism alterations in dendritic cells. Actually, I had more data and I didn't have time to put together, and I also want to be quite brief so that we can follow up with the current program. So these are the usual suspects, the virus that we are interested in studying, HSV1, HSV2. They're both similar viruses, but they're different. And they behave different in some minor aspects, but I think it's important still to differentiate them. So both are clinically relevant. They cause an important amount of diseases. I'll show you right away which diseases they produce. They are, I used to say big viruses, but after today's vaccinia virus, I think I'll have to start changing my wording. Still not bad. They have more than 80 genes. And you can see here that these viruses really don't care about exposing antigens to the immune system. They have 11 potential glycoproteins that they can show to the immune system, and they still coexist and persistently infect the host. So they clearly have the capacity to evade immunity. They're highly prevalent. Over 50% of population has HSV1, over 10% has HSV2. Infection, as all herpes viruses, is lifelong. And something that's quite interesting is that most infected individuals, 90% or more, are asymptomatic. But even though they are asymptomatic, they shed virus. So the virus is very successful in infecting the population, and that's why it can reach up to a 70% prevalence. Okay, so these are the different diseases produced by HSV. So it makes it also an interesting model because you can study viral infection in the brain, in the central nervous system, in the eye. You can also study infection in the mouth, in the skin, right? And in some more extreme cases, you can study infection in some inner tissues, but this is organs, sorry, but this is mainly in the case of immunosuppressed individuals. But you have different models, right? You can study different types of infections, and it's kind of interesting that you can have all these approaches with one same virus. So let me tell you that there have been attempts to make a vaccine against HSV1 and HSV2. Actually, there's an attempt that's been tried out the last 20 years based on a subunit glycoprotein-based vaccine, mainly on GD. And the approach is quite simple. It's GD combined with adjuvants, GD combined with other glycoproteins and adjuvants, or different forms of this glycoprotein plus adjuvants. And the results of these clinical trials, which were carried out by Big Pharma, you can see it doesn't show up here, but it was Big Pharma, GlaxoSmithKline. The data that came out from the clinical results phase 3, they were actually quite bad, very bad. I mean, the vaccine didn't work. So you only got a 9 to 20% effectiveness or efficacy. And you got these bad results even though you had neutralizing antibodies against GD, which was the aim of the study. So there's more than what was expected that is actually happening during infection. So what was the plan B? Given that this approach failed, what was the next second best bet in the line? Well, there was no plan B. So if you look at the amount of patients in clinical trials in the US during these years on the different approaches, vaccine approaches against HSV1, HSV2, you can see that 96%, 98% of all studies were focused on GB and GD-based subunit vaccines, and that didn't work. So there were only very few attempts here with mutant viruses. So if you are into immunology, you like vaccines, this is quite nice. You have an opportunity for vaccine development. And I believe, and I still believe until today, that attenuated virus approaches deserve more attempts. You've seen that with Mpox, the attenuated virus approach works pretty well, and we know that this works also in other cases for other viruses. So what mutant, what did we work on as an approach as a attenuated vaccine based on the virion? Well, we found some data that actually would argue against the use of GD as an appropriate antigen. So GD was reported to be non-protective in clinical trials, which is what I showed. It was also reported to negatively modulate T-cell responses, T-cell signaling, TCR signaling, T-cell apoptosis, and also modulate NK function. But at the same time, what was interesting is that GD was essential for virus entry. So what we did actually was create a mutant of HSV that lacks GD. So it has everything, all the glycoproteins, all its proteins, but lacks GD. It lacks the only protein that was being used as a vaccine approach for a vaccine against HSV. So it's completely against the trend. And you can see here that mice vaccinated with the GD mutant, I mean, you can challenge them with 10 times the lethal dose, 90, through intravaginal infection, genital infection, and these mice survive. And they have no neurological disease, and they have reduced amounts of virus in the genital tract or in neural tissue, and this vaccine actually works pretty nice as a vaccine. So this was done some time ago, and the big question for us, for my lab, was why is this vaccine or this mutant working as a vaccine? So we went into the mechanism. I had bet money that most likely the mechanism was mediated by T cells, but actually we would only get full protection when we would transfer serum from vaccinated mice into naive mice that were challenged afterwards with wild-type virus. Okay, so these mice are the only ones that survive, so protection is mediated by antibodies. And actually, if you measure antibodies, there's a huge amount of antibodies against HSV antigens. You can dilute the titer, the serum up to 1 in 800,000. So it's brutal, the amount of antibodies that you get. So what is driving these high titers of antibodies? Well, the central dogma of immunology says that B cells that produce good high affinity antibodies that are have effector functions are actually going this way because they receive good help, nice help from T helper cells. And these T helper cells have the correct phenotype to simulate the correct isotype of B cells, because these cells in turn get a good, nice activation, good response from dendritic cells. So this seems to be the source of the solution. So of course the question is, what is the relationship between dendritic cells and HSV? So if you look at the literature, you see that the virus does several things to dendritic cells. It promotes pro-inflammatory cytokines, inhibits autophagosome, inhibits MHC class 1 presentation, inhibits co-stimulation, but most importantly, you get this, you get apoptosis. So the virus kills the dendritic cell. And if you kill the dendritic cell, you won't have a nice T cell response because there's no dendritic cells to activate them. And if you don't have T cells, T helper cells, you won't have B cells, so you won't have antibodies, you won't have CTLs, cytotoxic T cells. So our focus is dendritic cells because these are the cells that carry out the downstream activation of immune components. So what we did is we cultured or we inoculated dendritic cells with the wild-type virus or the delta GD virus. And what we're measuring here is cell death. So you can see that if you grab dendritic cells at different time points and you infect them with a wild-type virus, these cells die. At 48 hours, you have 75% of cells are dead. If you inoculate these dendritic cells with the mutant, these cells at 48 hours are looking good. So you might say, that virus is a dead virus. So it's just acting like an inert particle. But actually, it is not. You can look at the proteins that the virus is expressing, and the virus is expressing proteins that are non-structural. So the virus is actively infecting the dendritic cell. It just doesn't kill them. So at some point, the cell can control the virus. And we went along with co-cultures. We co-cultured dendritic cells that were pulsed with the mutant virus and measured T-cell activation parameters. So we get nice T-cell activation markers, CD8, CD4, different markers. Overall, these dendritic cells can activate T-cells. Even if you grab these dendritic cells that are inoculated in vitro with the delta GD and you transfer them into mice, you can see that these mice that receive these dendritic cells, if you challenge them, if you measure immune components, they have nice titers against HSV antigens. And if you challenge them, they survive, not like those animals that receive the wild-type virus or receive other mutants such as delta GH or delta GD. Okay, and here neurological score looks pretty flat, and viral loads look pretty low. So that seems to be the mechanism, at least we suggest, that is how this attenuated virus manages to induce a nice protective immune response. We were also looking for specifically what within the dendritic cell was this mutant virus doing that the wild-type virus was not doing. So we looked for several things. We were really looking into the blind what was going on. And one of the assays we performed was to measure different UPR, unfolded protein response components. So this is a cellular response that's activated when the cell is stressed with too much protein production, as you would suggest occurs during viral infection. And overall, the only thing that you can see that kind of pops out is that actually the wild-type virus induces a XBP1 activation, not like the mutant virus. So we were actually looking, what does the mutant virus induce that the wild-type virus doesn't induce? And the response we got was just, there's nothing special with the mutant virus, but we saw this activation of the UPR response by the wild-type virus. And we didn't much pay attention to this for some years, until after some time, we said, you know what, we should look at this. This has not been reported. We should look, why is the UPR response activated in dendritic cells with the wild-type virus? So here are some details of the UPR response in the context of HSV infection. And actually, the literature says that the virus inhibits UPR response in infected cells. But we are actually seeing that the virus induces UPR response in dendritic cells. So there seems to be something specific about dendritic cells that is special and which could be helping that the virus can induce apoptosis in dendritic cells through the activation of the UPR response. So we put this to test. Here are two drugs that inhibit IRE1 alpha, which is one of the components of the UPR response. And as long as you add the inhibitors, you recover dendritic cell viability. So you infect the cells with the virus kills the cells, but if you inhibit the UPR response through IRE1 alpha, you recover cell viability and you reduce viral loads. So the dendritic cell can manage now the infection and actually live longer. And then we, of course, looked if these dendritic cells could activate T cells. And actually they can. They can induce CD25 expression, interferon gamma expression, T cell proliferation, and this seems to be mediated in some way by an increased expression of MHC class 1 in cells that are infected and treated with the drugs, while those cells that are infected with the virus but not treated with the drugs they have reduced MHC class 1 expression, so they can't activate T cells. So now these dendritic cells with a UPR response inhibited, they can. And these are different assays, again, that look at different parameters of T cell activation, CD4 T cell activation, in vitro. We have also looked at this in vivo. We have also looked at the profiles of these CD4 T cells and found that they have particular phenotypes, mainly Treg and Th17. We also looked at the migration of the dendritic cells. So what we do is in the foot pad of the animal here, we inject virus, we inject a dye, un colorante, a dye, and we inject the drugs. And we see whether the dendritic cells that are here migrate to the lymph node, to the closest lymph node, and that's a readout of the dendritic cell capacity to go and present antigens to T cells. So you can see here an increased migration of dendritic cells, and in vivo, if you measure CD8 and CD4 T cell activation, you get increased activation of virus-specific CD4 and CD8 T cells in vivo. Okay, this is the last few slides. I just want to show you that maybe I'm missing a slide between the previous one and this one, but there's recent literature that relates the UPR response with lipid metabolism. So there's data that says that the IR1 alpha pathway can lead to the activation of lipid metabolism genes that can alter the cellular lipid metabolism. And we're doing actually currently this link by measuring different lipid metabolism components in dendritic cells infected with the virus. And this image is quite shocking, actually. What we can see here is that dendritic cells that are infected with the virus have these structures, inner structures, that actually are compatible with lipid droplets, okay? And we can quantify these structures, and they're quite significantly present in infected cells, not so much in dendritic cells treated with UV inactivated virus or mock cells. If we go more specifically and we stain these lipid droplets with a lipid droplet dye, such as BodyP, we can actually see these lipid droplets in increased quantities in dendritic cells that are infected with the virus and not in dendritic cells that are non-infected or that are treated with the virus inactivated with UV. And you can actually quantify the number of lipid droplets per cell. They are increased here in those infected. You can also measure the area of the lipid droplets in the dendritic cells, and they're more pronounced. Okay, so we're actually going into more detail here. There's a lot of data that I'm not showing, but we've also done a lot of qPCR arrays of lipid metabolism gene expression, and we see that there's a huge amount of lipid metabolism genes that are activated in virus-infected dendritic cells. And this likely could be mediating this alteration in in the lipidic profile of dendritic cells. So that's what I wanted to show to you. So as a conclusion, we have so far identified a mutant of HSV that can be nice to dendritic cells and at the same time elicit a adaptive immunity, protective immune response. We found also that thanks to that study, we could see that the wild-type virus activates the UPR response in dendritic cells, mainly through the IRE1 alpha pathway, and that inhibiting this pathway, we can recover dendritic cell functions. And this is what's here. And that also, there's a line missing that's related to the lipid metabolism. And that relating IRE1 alpha to lipid metabolism, we likely have a pathway that connects both components, and we're further studying that. And that overall, by modulating host processes, such as the UPR, the lipid metabolism pathway, during infection of dendritic cells, we can establish a bottom-up adaptive antiviral immune response that could be protective. We're checking out this in animal models, but at least it's showing us that from the base, from those cells that are relevant for adaptive immune activation, those cells are recovering their functions. So as a takeaway message, even though obviously we have found some interesting findings, we believe that the relationship between herpes simplex viruses and the dendritic cells needs a more detailed analysis. We think that really that's the key relationship that needs to be improved so that you can get overall a nice, effective, adaptive immune response against these viruses. So this work was done obviously by young, talented students like you, and you're welcome, of course, to apply to write to us, to our laboratories, if you're interested in this type of research, if you would like to participate in our projects. And here are the different students that work in different projects. Some of them, of course, I cannot show because of time. And obviously thank collaborators that throughout Chile and throughout also some countries are helping us approach these questions in a more comprehensive manner. So thank you very much. Questions?
Thank you, Dr. Gonzalez, for your nice talk. This is short time for questions, please.
How specific that lipid effect on the immune cells is for certain symptoms or other viruses or bacteria that get inside the immune cells cause lipid accumulation? So there are in dendritic cells. We believe we will be the first to describe this. So hopefully the reviewers will think the same. So in dendritic cells, so you have some viruses that do induce lipid droplets in other cells, mainly hepatitis viruses. Their target is hepatocytes, and so they depend on lipid droplets for the replication cycle. But in dendritic cells, it's actually quite. It should be quite new. I haven't seen any report with viruses, and lipid droplets in dendritic cells. There are recent studies with dendritic cells in tumors. It does. So it's not a good substrate for the virus. So yield will give you, I don't know, will give you 1,000 times less or 1,000,000 times less virus yield than infecting a epithelial cell. But clearly there's an advantage for the virus in infecting these cells. And there's a nice literature of infection of dendritic cells with this virus in vivo, yeah. And some of it relates to what I've showed about relating of the migration capacity of dendritic cells. I mean, they're stalled right there in the infection site. They don't make it to the lymph node, so they won't activate T cells, and actually they die halfway. So we think that that's our first readout. If we have something that makes the dendritic cell recover viability, we move forward and we continue analysis, because at least alive dendritic cells, it will yield something, some response it will give. We just don't know yet if it's in all cases protective or not, but at least we have a live dendritic cell. Okay, yes. So without GD, all the antibodies are very rare.
Yes.
If you transfer those serum instead of the dendritic cell,
They're protective. So we should. Yeah, we showed it in that paper, that Eli's paper. We showed that actually we think they're mainly directed against GB. We haven't done the analysis. We did some Western blots, kind of like relate the location of the band as GD, but we did that. That's what we did. And it shows GD. It seems that they're mainly against GD and against other proteins, GB, and against other proteins, but we haven't done that analysis. That analysis was supposed to be done by a colleague who's a co-author of the work, but it hasn't been done yet. Yes. What we do know from this paper is that you do need Fc gamma receptor. So if you transfer this sera into a Fc gamma receptor knockout mouse, even the natal Fc gamma receptor, you lose the protection. That you need them for the protection, yeah. Okay, so we'll go on to the next speaker. The next speaker is is you? We'll check. Go ahead. We'll see. So I think they'll project to the next presentation. That will give us the name of our next presenter.
Ah. I'm coming. ¿Te lo presento?
Ahora le toca a...
Eso es bueno.
a la otra, ¿no?
Sí.
Ya.
¿Te lo presento?
Sí, yo lo presento.
Ya.
Gracias. Muy buenas tardes. Continuamos entonces con este simposio. A continuación corresponde la presentación de la doctora Susan Bueno, inmunogenicidad de una vacuna inactivada contra el SARS-CoV-2 en personas de Chile. La doctora Susan Bueno es profesora titular de la Facultad de Ciencias Biológicas de la Pontificia Universidad Católica de Chile, investigadora del Instituto Milenio en Inmunología e Inmunoterapia. Doctora, le invitamos a subir al estrado.
Directamente al micrófono. Perfecto. Ok. Mientras carga mi presentación, muchas gracias a los asistentes por estar en esta charla. Voy a dar mi charla en inglés, ya que tienen traducción y pueda interactuar con los speakers también.
Well, my presentation in this symposium, it's immunogenicity of an inactivated SARS-CoV-2 vaccines in people from Chile.
And today I'm going to talk a little bit more about some research that is very near and dear for our heart in the Institute, because it's the evaluation of the inactivated SARS-CoV-2 vaccine in children. And this is very important because Antofagasta work and contribute to this study with the cohort of children as well. So as an introduction, just to stress again that the vaccines are one of the most cost-effective strategies to control infectious diseases. And actually, when we were in the middle of the pandemic, a good news arose that at August 2020, that the WHO and UNICEF announced that one of the countries in Africa have eradicated the poliovirus due to vaccination. Of course, the poliovirus, as we remember, is a virus that can target the nerve cells. There is a oral vaccine that relates with the introduction and the coverage of this vaccine around the world, is significantly reducing and eliminating this vaccine from human populations. So these pictures where the children with paralysis due to this virus is for us like kind of a story, especially in Latin America. But we are in a current situation that we are fighting now with another virus that is causing pandemics and a lot of disease in the world. We know that this virus had spread very high all around the world in very short time. And we have these very hard images to see when we have the loss of many lives around the world due to this virus that caused this severe disease. And this has been one of the infectious diseases that has come to the first for the top cause of death around the world. Since infectious diseases have been like in the fourth or fifth cause of disease of death around the world just before the pandemic. We hopefully seen that in the future these images will be also part of the story, and we know that vaccines can contribute highly to this goal. So as we know, the COVID-19 and most of the respiratory tract infection caused by viruses could produce a rate of severity in the population. Some people develop with viral infections a mild disease.
with a very specific symptoms that can be resolved very quickly. Other people can compromise more pulmonary tissue and cause more severe disease. And some that is a low percentage can cause critical disease due to a polyinflammatory disease. As I said, this is a low amount of the population, low percentage, but when all the whole world is susceptible to this infection, of course, these critical cases are huge and cause a lot of stress in the public health system all around the world. So what happened when in Latin America with this disease? We know that all the countries in Latin America had been affected more than others with this infectious disease. And by October this year, we have a total of 1,000,006, at most 1.7 million deaths in Latin America. And this is not only is caused will be caused by COVID-19 or SARS-CoV-2 specifically, but this pandemic has also impacted some important programs as the vaccination programs for children that can, in the long term, also cause more problems and more morbidity and of course, deaths and loss of life of children. So when we got a new disease that everybody is susceptible to that, there are several ways that we can deal with that. First of all is that know how to prevent the transmission, isolation, identify the sick people, and also apply measures that prevent the spreading of the disease. Also identify treatment. For instance, in the case of COVID-19, there was the early use of corticosteroid, trying to develop and use previously developed antiviral drugs. And this is a classical approach as well, is to use passive immunity when we recover the sera of people that already had the virus and recover, and then have these sera available for the most susceptible people. Unfortunately, all these measures is one way or the other can help to control the disease, but definitely vaccination and the acquisition of immunity in the community, it's one of the most important way to prevent and advance in a pandemic like COVID-19. So we are aiming at getting herd immunity in order to prevent or reduce the load of infection, and then just dealing with a low number of critical patients that will require the most important measures for and resources for the public health. So in the terms of vaccination, if we go to Chile, we have a strength and weakness. One of the the strength that we have is a strong vaccination coverage. What is showing here is a map when we show, or is shown, all the vaccination points or different places where you can get vaccination of the national immunization programs. And as you can see, all along Chile, we have coverage, even in the Easter Island, to apply the vaccines that is provided by the population for the population by the government. So the coverage is very good, and also we have a very robust schedule of vaccination for people from for the beginning when they get burned until with birth until the elderly. For instance, people that is 65 years old and older. So everybody, as you maybe remember, we know that, or the people don't question that you are in Chile and you have this program, and there is a very strong and very organized ways to vaccinate the people, and it is a good thing because we got a lot of adhesion for the population for vaccines. But our weakness is that we don't have a local vaccine production. So this is something, a pain that we have in our country and that we have been trying to address. And this is why we are here. That is the why we are doing this collaboration with the people, with the researchers in Antofagasta, in Santiago, and other places in Chile, in order to bring again the capacity to produce our own vaccines and not only depend on vaccines that are produced abroad. So in Catholic University, we have been working for vaccines against RSV for more than at least 2 decades. And we have working with 3 laboratories. The two researchers are here, Pablo Gonzalez, myself, and Dr. Alexis Kalergis, that is the director of the Millennium Institute of Immunology and Immunotherapy. And we advanced to produce a recombinant vaccine for RSV, to produce a GMP grade vaccines in order to run the first phase 1 clinical trial in Chile for this vaccine. We already go ahead with that. We published the results. We got very good results, and we are aiming to move forward this vaccine. And we were working on that when we go for a meeting in Beijing, in China, in 2019. So we meet in person with one of our collaborators, and the ones that we wanted to collaborate in the RSV vaccine, that is Sinovac. It's a Chinese company that is specialized in producing vaccines. And we were discussing the possibility to run a phase 2 clinical trial in China with our vaccines. And then this virus arrived, the SARS-CoV-2. So all the capacity of Sinovac, of course, it was oriented to or refocused to the production of a vaccine for SARS-CoV-2. And they produced this inactivated SARS-CoV-2 vaccine that is no other thing than the virus producing cell cultures that are inactivated by chemical treatment. And then the virus is not able to infect or replicate the cells, but it still get all the components that they are recognized by the immune system and can induce immunity in the population. This vaccine was, and the data was published in 2 important journals, Science and The Lancet. And this vaccine, in order to move forward with this vaccine, it needed to be tested in further clinical trials. So as a collaborators and knowing the capacity that we have here in Chile, Sinovac contact us and we collaborate with this vaccine, which is an activated vaccine that is a traditional vaccine, as I mentioned before. We were very confident about that this platform will be a good idea to go for the prevention of COVID-19. First, because the inactivated virus is a previously tested platform for vaccine development that has been used in humans for a long time. And we know the safety profile that these kind of vaccines have in the population. The storage conditions are compatible with health sources in middle and low income countries as Chile and Latin America, that we do not have until SARS-CoV-2 the ultra freezers to store vaccines, and even if you need to transport these vaccines to very rural areas, it's much more convenient to have a vaccine that can be stored at 4 degrees. And also, one interesting thing for us as immunologists is that an inactivated whole vaccine can induce an immune response not only to one antigen, but different antigens that are included in the viral particle. So with Catholic University and Sinovac, and memorandum of understanding and then an agreement of collaboration and work with clinical trial to test this vaccine was launched. We got a ceremony of signature with the top authorities, and we move forward this collaboration in order to run the clinical trial. And is this vaccine proved to be safe, effective, and immunogenic, and approved by the a regulatory agency in Chile, Chile will have the possibility to get amount of vaccine required to vaccinate all the target population, and a low price and a preferential access. That this one of the main points that during a pandemic, everybody needs to ensure and secure for their population. So we launched this clinical study, and the results that we got in the clinical study for the adult population, I discussed 3 days ago with the results that the vaccine is safe, immunogenic, and this was data was published in several journals that you, of course, can review and see the details of the science doing here. But still, when we got this vaccine already approved for the Chilean population and start the vaccination rollout, there is still a population that was with no protection, that is children, because this vaccine was approved from 18 years and above. So we decided to move forward as well with a clinical trial for a pediatric population and children younger than 18 or people younger than 18 years old. So we launched this pediatric study when we also joined together with other countries that were doing a multi-country study in order to test the safety and the immunogenicity of this vaccine in children. So this study, as I mentioned here, includes 5 countries: Chile, Kenya, Malaysia, Philippines, and South Africa. And the first design included 14,000 volunteers recruited and randomized that included a vaccine arm and a placebo arm. And in Chile, we move forward with the vaccine arm, and I'm going to explain in a moment why we did that. And we included this number of volunteers vaccinated in Chile from 3 different age groups: the 3 to 5 years old, 6 to 11 years old, and 12 to 17 years old. We first started working with the placebo arm, but just right after we initiated the study, the vaccine, the Sinovac vaccine, was approved for adolescents from 12 to 17 years. So when a vaccine is available for a group, you cannot use placebo for this group of people. So we decided to keep our study still in the multicentric study, but just with the vaccination group. And our aims was of course of the whole study was to evaluate the efficacy of 2 doses of CoronaVac and the prevention for COVID-19 symptomatic. That this is the main aim of the whole study. But in Chile, we evaluated mainly the immunogenicity of CoronaVac and also the safety of this vaccine. So we evaluated the local and systemic adverse events in the first 7 days, the serious adverse events or events of a special interest, and the immunogenicity. Today, I'm going to show you a little bit deep what we did in our laboratory regarding the immunogenicity of the vaccine in the population. So we included a subpopulation of 313 people for the immunogenicity arm, and to evaluate both the T-cell immunity and the antibody immunity. We were working together with the approval of several vaccines for the pediatric population. So the data I'm going to show you here are the data for visit 1. That is, the visit 1 is when you get the blood sample before vaccination, and visit 5, that is the sample that you get 4 weeks after the second dose. And this is the schedule that we use. The visit 1, as I mentioned before, we got the first the sample at just right before the moment of the first dose, and we got a sample from blood and saliva. We got a sample from saliva at day 28 at the moment of the second dose. And then we got a second sample of blood at day 56, that is 4 weeks after the second dose. And also this study included a sample 6 months after the second dose. We got samples for PBMCs, or whole blood with the anticoagulant to get the white blood cells, and also for plasma in order to evaluate the antibodies. I'm going to focus mainly in the antibodies and also the PBMCs in the blood. So our first study was to evaluate if the vaccine is able to trigger antibodies in the children, total antibodies against the spike protein. And in collaboration here with the hospital in Universidad de Antofagasta, we evaluated the level of SARS-CoV-2 total IgG that the vaccine triggers in the group of 3 to 11 years old. In this case, we fused together the two groups for the number that we evaluated at that time, and also the group of 12 to 17. And as you can see here, some of them have already been exposed to the virus, and of course, we wanted to include in order to see that even if the symptomatic infection was a cause of exclusion of the study, still asymptomatic is not possible to exclude in the rapid test. So we still get some people at the black dot are the sample at the first visit one, or the moment that they get the vaccination, and the green dots are 4 weeks after the second dose. And as you can see here, they are most of the evaluated people or children trigger a total IgG vaccine. So we also evaluated neutralizing antibodies, and we have several ways to evaluate neutralizing antibody. First is in cell culture to evaluate the capacity of the antibody to prevent that infected virus get into the culture cells. We do that with Sinovac and also with the Instituto de Salud Pública, that is our very huge collaborators. And we also have techniques that allow us to evaluate the capacity to block the interaction of just the RBD, if the spike protein, to a ACE2 receptor that is adhered to a plastic well here. And this is a study that you can do very quickly with no virus, with no requirements for BCL3 facilities. And we do it here we do it in Catholic University. And the good thing about this is that we can express our data in international units and can compare with other techniques on other vaccines. And what we observe as equivalent what we see in the with the total antibodies, the antibodies that are able to prevent the interaction with the spike protein with the ACE2 receptor, all increase in this 2 age group. As you can see, the positivity in the 12 to 17 years old is 100%. In the case of 3 to 1 years old, just one individual didn't get a good response of a neutralizing antibody. All of them get a very good response. And when you compare that, this is very interesting, and I wanted to share with you. If you divide with different age group, and we compare with the results that we got with the same technique in the group of adult people, you can see that the younger had a stronger response for neutralizing antibodies than the adults. And this is something that was also seen in China in the study that were done by Sinovac. And we also have a significant difference between the 3 to 5 years old as compared to the adolescents, that is the 12, or the teenagers, in this case, 12 to 17 years old. And also the teenagers seem to trigger a higher response than the adult population. Here we have until the 59 years old, that was our threshold. If we use the alive virus as well, we also have the same pattern that using the technique that allow us to see the infected virus is prevented to enter the infected cells. What you see again is that the younger population trigger a higher response than the older population, the teenager and the adults. This study was done in the Instituto de Salud Pública, and this is our main collaborators, Eugenio Ramírez, Rodrigo Fache, Jorge Rodríguez, Fernández, and Judith Mora. They have been helping us to doing these assays that are very time consuming, and they have been very amazing with us. Also, we have been working with the T-cell response of these people, of these children, and for that we have been working with the La Jolla Institute for Immunology that provide us the proteins of the virus, but segmented in very small pieces that is called peptides. And it's not only one few peptides, it's an overlap of several peptides derived from all the proteins from the virus that are divided for peptides for the spike protein and peptides for all the other proteins except the spike. And also we get commercially other mega pool of peptides that are called this technique or this reagent for specific structural proteins of the virus. We can evaluate by ELISpot. That is a technique that allows us to count the amount of cells that produce interferon gamma, that is an antiviral cytokine that is produced when the T cells are able to recognize some of the peptides derived from these proteins, so are SARS-CoV-2 specifics, and also for flow cytometry. And in this case, what we observe is in the surface of these cells are expressed some activation markers where the T cells recognize some cells presenting these peptides. These assays were the ELISpot were done in Catholic University, and all the flow cytometry data was done in Chile University in the laboratory of Dr. Leandro Carreño, that is also here with us today. And Alessandro Sete, Daniela Weisskopf, and Alba Grifoni, that you hear her in the morning, were also very excellent collaborators that were very generous to share these materials that are, of course, very hard to prepare and very expensive to distribute around the world. So it's been a very nice example of collaboration and advancing science. So what we see with the ELISpot is that we see for the spike protein that the group that is 12 to 17 years old, we see a significant increase in the cells that produce interferon gamma after the stimulation with the spike protein. And we don't see much difference when we stimulate with the other proteins that are from the virus. And what we think is that in the younger population, we still have a strong response that is triggered by other related coronaviruses that can share structural similarities with SARS-CoV-2, and that is the reason that, as you can see here, we have in the premium a high response in this population. For flow cytometry, we see something equivalent, and what you can see here is that we have the group of 3 to 11 years old and 12 to 17 years old, and both groups were able to produce higher activation markers for when they are stimulated with the spike protein, but only in the 12 to 17 where they are stimulated with the M protein, and for the M protein or the total protein except the spike, we see a significant change in the activation markers in these cells, indicating that the vaccine is able to trigger a T-cell immune response. These cells also produce some specific cytokines like the IL-2, that is a cytokine produced by T cells when they get activated for most of the peptide, except for the R. In the case of the younger population, we get a significant increase in the secretion of these cytokines. And in the case of interferon gamma, we observe an increase, especially in the group of 3 to 11, but still we get, as we observe with the ELISpot, a low response. Also, we collaborate with the laboratory of Dr. Ricardo Sotorrifo in the University of Chile that have set a system to produce pseudoviruses that are based on HIV, but express the spike protein in the surface and allow us to evaluate also neutralization. But why we use this system as well is because it allows us to produce viral particles that had the spike protein from the variants of concern and allow us to evaluate the response of the vaccine or the antibodies triggered by the vaccine to the variants of concern. And what the lab of Ricardo Soto did is to generate a virus that produced the spike protein that is from the original strain or the ancestral strain, a virus that expressed the spike protein from the Delta variant, and another one that expressed the spike protein from Omicron variant. And we test the sera from the plasma for the children that were obtained 4 weeks after the second dose. And as you can see here, we have an increase in the neutralization for the spike protein for the ancestral strain. We start to see close to 2 times less neutralization for the Delta, and at least 16 times less neutralization for the Omicron strain. And that is the reason that the vaccine can prevent the severe disease, but are not able to prevent the transmission of the virus and that you can catch the virus. When we separate this with the age group, we still see equivalent results, that we see a reduction in the capacity of the antibodies triggered by CoronaVac in children to neutralize, especially the Omicron variant. But the good news is that when we evaluate the T-cell response, and also this is in collaboration with the La Jolla Institute, that they provide this mega pool of peptides derived from the spike protein from the original or the wild type strain, the mega pools of peptide derived from the spike from Delta and the spike from Omicron. And as you can see here, that we see for the T-cell response that were evaluated by flow cytometry, that there is a slight reduction in the T-cell response that recognize the Delta spike, but 1.3 times less, and this is a no significant difference. And in the case of Omicron, and we are still studying that, we don't have an answer yet why this is happening. We see an increase in the response of T-cell response for the Omicron variant. That is plus or 3 times more response that we see with the wild type strain. And when we separate by age group, as you can see here, the younger people is the one that had the higher response for Omicron. So the take-home message is that in this case, when a new variants arise, the capacity of the antibodies is reduced to neutralize the virus, but the T-cell response is get stable. So it is still the vaccine is preventive for the severe disease caused by these viruses, unless we are in front of a person that has problem with immunity and treatments that can prevent the correct function of the T-cell response. When we evaluate the antibodies that were induced by the against the wild type, the Delta and the Omicron, we still see a reduction, as I mentioned before. And in this case, we separated by 3 to 5 years old and still have a good response, but in all the cases, we see a reduction for the Omicron variant. But when the kids get infected with coronavirus after vaccination, what we observe is an insignificant increase in the level of antibody post-infection. A high amount of these antibodies, especially in the case that you can see here, very low response for the Omicron variant, but a huge response after infection. That indicates that, of course, the vaccination triggers a memory that when you confront the virus, readily start to produce higher levels of antibodies that can, this is what we are evaluating, how long they last. The important thing is in that cases, we just have here a preliminary data with 8 breakthrough cases. In that these cases, the data was produced by Daniela Rivera, which is a PhD student in the Millennium Institute. The important thing is that all the cases were very, very mild. Also, the T-cell response seems to start to increase a little bit, especially for the spike protein. So the responses still can be things as protective. So as conclusion, we detect an increase in the IgG antibody titers after CoronaVac immunizations in kids. The administration of 2 doses promote the neutralizing antibodies against this virus. 2 doses of CoronaVac promote the production of CD4 positive T cells specific for the spike protein and other proteins of the virus against different antigens. The administration of 2 doses of CoronaVac promote the induction of antivirial cytokines such as interferon gamma, but in the case of kids, as compared with the adults, we see less pronounced production. We observe an increase in the cellular response against the Omicron variant, and is observed in subjects that were vaccinated with the 2 doses, especially in the younger groups. But this phenotype is not equivalent to the neutralizing antibodies, so we are interested in studying a little bit more about that. And our preliminary data show that infected subjects increase the secretion of neutralizing antibodies against variants of concern and slightly increase the induction of the cellular immune response. And this is something that we are working, is work in progress. So that just to remember you that these effectiveness assays indicated that this vaccine was preventive for COVID-19 symptomatic, for hospitalization, severe disease and death. And the booster dose increased even more the effectiveness of this vaccine. Unfortunately, in our study, we do not keep working to evaluate the booster dose in pediatric population because at that time that everybody in the community was open to receive a booster. And one important thing is that the data that I show you today was relevant for the approval of the vaccine in the younger population, 3 to 6 years old in Chile with CoronaVac. So the vaccination rollout started in Chile very quickly, also as a country. And our data was also discussed with Anvisa, which is the regulatory agency in Brazil, that also evaluated and taking into account our result to approve the vaccine in Brazil to immunize the Brazilian population, the children. That is most probably the most big children population in America. So I would like to end thanking and acknowledge the collaboration and the work done by Sinovac, the government of Chile, and the Confederación de la Producción y del Comercio that allow us to that fund this study, de Facultad de Medicina de la Universidad de Chile, el Instituto de Ciencias Biomédicas, Laboratorio del Dr. Leandro Carreño, Ricardo Sotorrifo, la Joya Institute for Immunology, ISP, el Instituto de Salud Pública, PAT, that is an organization, our ONG, that allow us and was closely following us, our study, to give us advice and provide funding as well. The Millennium Institute for Immunology and Immunotherapy, the team of people that were working during the hardest time of the pandemic in this study, the clinical team, and the nice collaboration that we established with CoronaVac and our laboratory to do science in vaccines. And this is the team that worked in this study. Alexis that cannot be here, but as I mentioned before, he apologized and was very sad he cannot come. But because this is a very important project for us, Pablo González, Leandro Carreño, Jorge Soto, that work in the study, the direction of the study, and also in the scientific part of the study, the clinical team and the pharmaceutical team that is also really important when you are doing a clinical study for the management of the vaccines and all the correct administration and storage. And just to remember that it's very important for us to remember that the vaccination started in Chile thanks in a big part for this study that we did with CoronaVac in Chile. And thank you for your attention. And we still feel very proud that we contribute to the vaccination with the elderly that were the first one that started the vaccination in Chile, and the children as well. So thank you very much. Preguntas or questions? Valeria.
Gracias por su presentación, doctora Susan. Me pregunto, o se han preguntado, está entre la intención o cómo podría compararse qué ha ocurrido en nuestro país, porque es una situación bastante particular que recibimos primero 2 dosis de Sinovac y vinieron refuerzos de Pfizer, versus lo que ocurre en otros países que recibieron solo Pfizer e incluso recibimos mezclas de otras vacunas. Pero especialmente para los que recibimos dos dosis de Sinovac, considerando que es un virus inactivado, ¿qué ventajas yo pensaría que tendríamos una ventaja sobre quienes recibieron solo la vacuna de RNA mensajero? Yo pensaría, pero sería interesante evaluarlo.
Sí.
¿Lo han considerado?
No, nos encantaría. Actually, the question is whether we have evaluated how was the effectiveness in Chile regarding, because we got most of the people to vaccination with CoronaVac and then heterologous vaccination with other platforms, whether we have some advantage in terms of protection or effectiveness regarding to other countries that only receive one kind of vaccine or other platform. And this is a super interesting study that we would love to do. This, of course, needs to do some effectiveness in whole population study, like real world study, that what has been occurring in terms of effectiveness and for different manifestations of the disease, death or infection, and even some long-term consequences. But yes, we are not aware of a study that compares the protection or the parameters that provide CoronaVac with respect to other vaccines in the world. Maybe at the beginning, you can do that with the 2 doses, but after several other doses and see whether we have some specific protection or how it compares to the, for instance, the variants of concern. I'm not totally aware of but probably David has some idea about that. No. Okay.
Y otra.
¿Sí?
Otra. Ahí sí. ¿No? ¿Sí?
Ahora sí.
Sí, ahora sí. Al respecto, considerando los hallazgos de la respuesta celular frente a otros antígenos que no sean Spike, ¿se ha considerado evaluar una vacuna multiepítope que tenga algunas de estos elementos?
Sí, so it's a very good question. It's regarding whether it's been evaluated or projected some vaccine that not only include the spikes, but other antigens. Maybe Lindsay can take a little idea about that in his presentation, whether there are other multiple platforms that can include several epitopes of the different, for a same protein, for instance, but of course could include other proteins. But as long as I'm aware, all of the vaccines have been target the spike protein. That is the most important protein for viral infection.
Gracias.
Okay.
¿Preguntas? Creo que no.
Gracias.
Muy bien, agradecemos a la doctora Susan Bueno por su exposición. A continuación, el doctor Lindsay Chang realizará la exposición Inmunización intranasal con vacunas contra la infección y transmisión del SARS-CoV-2, el objetivo último y los desafíos por delante. El doctor Lindsay Chang es profesor y director del Comprehensive AIDS Research Center, del Center for Global Health and Infectious Diseases, de la Escuela de Medicina de la Tsinghua University en China. Invitamos al doctor Lin Chi a acercarse al estrado.
Okay. All right. Okay. Well, while the slides is being loaded, I have to thank the organizer for your kind invitation to be here. You know, over the last few days, I had a luxury to visit the university, beautiful country, beautiful people, and a very exciting scientific change. So the whole purpose for me to come to Chile, this is my first time, is to learn what the whole team has been doing and try to find the best opportunity to collaborate. Okay, so with that, I felt fit right in after all the previous speakers talking about bacteria pathogens, one viral pathogens, and another, particularly Susan's COVID-19. So what I'm going to talk to you about is the intranasal vaccine against diverse SARS-CoV-2 variants. This is a big topic because the whole purpose of this talk is try to develop something that we could prevent the viral infection and the transmission. I have to admit this is just the work ongoing in process. And then hopefully the vaccine that we're doing will allow us to prevent SARS-CoV-2 infection. Like every previous speakers, that before we develop a vaccine, we have to understand our enemy better, as clearly as possible, so we could devise a better strategy to prevent or to attack this pathogen. So this is a coronavirus, a real coronavirus, actually derived from an inactivated vaccine. And then we put it under the electron microscope and see it in an anatomic fashion. So as Susan pointed out, this virus, that diameter is just 70 to 100 nanometers. And then this highlighted in the blue is in fact the viral membrane that's holding the viral particle intact. Within the blue sphere or the circle, there's many yellow balls. That's the M protein that's cover the nucleic acid inside to protect the degradation of its genetic material. On the surface of this blue ball, you can see there's a red and a dark brown spikes. Those are the spike protein that Susan talked a lot about. And those for a given, as we know now, for a given viral particle, a real SARS-CoV-2 particle, there are about 24 minus plus those spikes on each viral particle. And then those highlighted in red is in the one structure conformation. Those highlighted in the brown is another structure conformation, which means those structure is not stand still. They fluctuate from one position to another, allowing this protein to be able to bind to the receptor and then initiate the entry process. So those spike proteins are very important for binding to the receptor and also a major target for our antibody recognition. So that's why when you make a vaccine, there's many ways you could make it, as Susan just presented, inactivated form. But there are many other recombinant proteins, mRNA-based or vector-based vaccine that are targeted mainly to the spike protein highlighted here in red. During the early outbreaks, because my laboratories and the structural biology laboratory in Tsinghua University has a long history of studying coronaviruses, including SARS-1 and MERS, that's identified in 2003 and 2012, respectively. So what we have, given the technology platform we have, we were among the world that identify the crystal structure or resolve the crystal structure between the part of the spike protein called receptor binding domain, here highlighted in the cyan color, and the red color, and the receptor ACE2. So resolving this really crystal structure allow us to see how the green interact with the CN. That's highlighted in the interface is red. And this structure-wise is very similar to the ACE2 interacting with a SARS RBD. So very much similar. But the region highlighted in red, despite of a structural similarity, there are about 50% differences between SARS-1 and the SARS-2. So many of the immunity that we generated against SARS-2 or SARS-1 are very strain specific. There are some degree of cross-antibody reactivity between SARS-1 and SARS-2, but majority of them are very strain specific. So this really allows us to understand from the virus perspective, oh, this region playing a very important role in interacting with the green, which is the cellular receptor, ACE2. Once we have this structure, we also use this RBD as a bait to fish out the antibodies from the convalescent patient to see whether we are able to isolate any monoclonal antibodies from infected patient. The whole purpose of isolating antibody from patient is to understand our antibody reactivity to the virus, to see whether we are able to clone out some of the good antibodies and our understanding our antibody response better, so we could design better vaccines to induce stronger, broader, or long, durable antibody response. So as you could see, the protein in the middle, the C in color, the light blue, is the portion of the spike called receptor binding domain. If you remember the previous video, this CN color, blue, is interact with the green, because that's a critical for virus attach to the receptor and get into the cell. But what I highlight the other color is the purple and the yellow. One pair is one antibody. As you can see, we have a 3 antibody crystal structure resolved that's attacking the blue or the viral protein from different angle, binding different positions on the RBD. Because they bind to the different region of RBD, they show dramatic difference in their activity in blocking viral infection, suggesting our antibodies are distinct, are different. So what we did was we select the tool that's really good in neutralizing activity and develop the first China antibody drugs against COVID-19 and approved by the China FDA. But regardless of that antibody drug, we realized the RBD is not only important for viral getting into the cell, but it's also a major target for neutralizing antibodies. So this is going to serve as a critical reference or critical guidance for us to develop the next generation vaccine that perhaps able to block viral infection and the transmission. So let's come back, have a little general view about the current situation of COVID-19 vaccine. As Susan said, and many others suggested, we had achieved tremendous progress in the last 2 to 3 years in terms of developing many kind of COVID-19 vaccine, including inactivated vaccine, vector-based vaccine, mRNA vaccine, a protein-based vaccine. So that has prevented high efficacy in terms of preventing hospitalization and death. Amazing progress within a short period of time. However, but there's a big but. All those vaccines, although able to prevent disease and hospitalization, but none of them is able to prevent acquisition and the transmission. That's why there's so many breakthrough infections, despite of continuing booster, 3rd dose, 4th dose. So what will happen if they cannot prevent from acquisition or transmission? So the the dear and the direct consequences include, but not limited to, the following four areas. Say, if it's not able to prevent transmission and acquisition, it will continue to replicate and transmit. You give the virus the opportunity to generate mutations that escape from our immune recognition, including those induced by the vaccine, and then continue to compromise our vaccine efficacy, and then continue to pose risk on our health and also social economic development. So not able to prevent infection and acquisition or transmission is a big deal. So the whole world, the scientists in the whole world are trying to develop next generation vaccines that achieve a better or higher, perhaps more difficult roles in terms of preventing acquisition and transmission. The reason behind the current vaccine's failure in protecting the transmission or acquisition is largely depend on, because of two reasons. Largely, there's many other reasons. One is the continuous emerge and the spread of the SARS-CoV-2 variants. As we all know very well that after about a year of a pandemic, many different variants began to emerge, such as alpha strain emerged in the United Kingdom at the end of 2020. And then early 2021, gamma strains, beta strains emerged in South America, particularly in Brazil. And then November 2020, not November 2020, is actually early 2021, the Delta strains initially emerged from India. And then end of 2021, multiple subvariants emerged from South Africa, Botswana, and particular in the South African continent. So those mutations, as you can see, each one of those big thing represent a single trimeric spike on the viral variants. And those red dots on each of those variants recognize the number of mutations that occurred compared to the original Wuhan strain. So generally speaking, you can see the number of red dots increase from the early alpha strain, beta, gamma, delta to the Omicron strain. So there are about 35 above single mutations identified on the Omicron strain. That's really allowed the virus to escape from many antibody recognition. So we have, because of this, many efficacies of vaccines has been dropped. Just like Susan showed, inactivated vaccines in some cases drop 18-fold, sometimes 7-fold, right? Similar drop in antibody titer has been shown for mRNA and for vector-based RNA. And many of those mutations also escape the T-cell responses, although T-cell response in general are much more stable. So that's offer some hope while we are struggling with the T-cell, with the antibody response. Another potential reason that our vaccine is losing its efficacy is because our antibody response that induced by vaccination or by infection do wane down over time. They don't persist at a higher level. That's very natural, because once vaccine antigen or viral antigen removed by our human body, we don't need that high level of armory around. That's a waste of resources. So this response comes down. Together with the mutant, that's why there's so many breakthrough infections. As far as I know, even my family members got infected twice or 3 times. So the immunity induced by vaccination and infection or hybrid immunity are not able to protect from infection. One possible reason could be many of those vaccines were administered through intramuscular immunization, right? So all of them. So there's a big vacuum that existing in this vaccination strategy. Now the question comes to, okay, so if through intramuscular immunization, we are not able to prevent infection transmission, rather if we could boost up the intranasal or respiratory tract immunity at the site of a viral entry, are we able to induce type of protection that we all needed? Right, that's a big question. That's $1 million question. It's not a trivial question because a lot of scientists began to work in this area, tries to boost the immune response of here. Because at the mucosal level, you have a lot of T cell responses, you have a lot of antibody responses. In particular, at the mucosal surfaces, you have a dimeric IgA that really shows a stronger binding, a stronger neutralizing activity. So the key question is, are we able to make it? And then this consensus has been reached among the scientists globally, not just me. You know, I'm talking about, it sounds like my idea. It's not my idea. It is the common goal of all the scientists in the world. I hope become part of your goal among the students. So this person is very well known. The NIAID director in the US and the US President's chief advisor on COVID-19. So what he said was, the next generation coronavirus vaccine that be administered by nasal or oral mucosa for the sake of protection of transmission and acquisition. And then not only against severe diseases that protect against acquisition and transmission. So this is exactly what I was just repeated. And then apart from Fauci, there's many other scientists in the field also argue for the same point, because without that, you will continue to allow virus escape. And then from your vaccine, we'll have to have this vicious cycle to repeat ourselves to chase the virus. That's going to be a tiring and a non-effective way of dealing with this virus. So what's happening in our pursuit of intranasal vaccines? So there's actually over a dozen of vaccine candidates being tested through intranasal administration. And then I have to say many of them fell into the category of adenovirus-based strategy or live attenuated virus strategy. So there is this increasingly become popular, live attenuated or live virus that could be attenuated for the intranasal immunization. So now come back to the dear question that we all ask to ourselves. Can we design or develop intranasal vaccine to induce broadly protective vaccine? Broadly protected, that means not just protect a wild type, but also protect the variants, or even broader, sarbecoviruses, or including other cytopathic humans pathogenic viruses like SARS-1, SARS-2, and MERS. So this is a big, big question. So when we look into the designs, we have summarized many published data, structure-wise, antibody-wise, from our own lab and from the lab around the world. So what we find was RBD is a major target. That's everybody agree. But if you dive into RBD and then put all the antibody together, so what we find was, despite of many mutations, despite of substantial escape from our antibody response or antibody recognition, almost every class you have antibody that able to maintain the neutralizing activity against all variants we identified so far. Alpha, beta, gamma, delta, Omicron, BQ1, XBB. That's amazing, suggesting this is really a major target we should focus on. You know, we could only do some. One laboratory could only do some, so we have to pick a fight. When we pick a fight, we pick the RBD as our target. Okay, maybe different laboratory trying the spike protein. We also have a trimeric spike protein design for the same purpose. But what I'm going to show to you is RBD based the one that we are trying to push into clinical development is a spike protein based. So RBD based has been tossed around and tested around by many different laboratories. In the United States, I could name a few that are really moving forward. One is from the Washington University in Seattle. The Neil King Laboratories in Seattle has already developed a nanoparticle-based RBD vaccines that's collaborated with a Korean company that already entered into a human trial. That's a nanoparticle-based vaccine. And then Caltech is also generating a nanoparticle-based vaccine that has not been collaborated or entered into clinical trial, but show a very promising protection in the in vivo animal data. And then there's a group in Duke University using the ferritin as a carrier protein to generate a nanoparticles that already tested in monkey offer a tremendous protection against diverse coronaviruses. So this strategy is pretty amazing. So I think we are on the same track, but they are moving a little ahead of because they are started early. But one thing related to the nanoparticle, when you do a manufacture, nanoparticle is actually very complicated. When you do manufacture, you do a quality control, quality assurance processes. Each step, you have to be absolutely sure about your quality, about stability, and about many other measurements. So what we did was, since we are very familiar with the structure base, with the structure design. So what we did was we designed the RBD structure into the head-to-tail connection plus N proteins with only one gene. So only one expression allows us to have the 3 head-to-tail RBD connected and the 4 RBD connected. In this RBD, so as you can see, for the 3 head-to-tail RBD, we have the SARS-1, SARS-2, and the MERS. And for 4 head-to-tail connected RBD, we have SARS-1, SARS-2, MERS, and Omicron RBD. So this result has not been published, but it's very exciting in the animal. But this is only in the animal. Whether it's going to pan out in the end is another question. So what we did then, because we want to have an intranasal immunization, adenovirus is one of the best vectors that's been tested and being studied in humans through intranasal immunization. So take advantage of what we have, and we put those 3 head-to-tail or 4 head-to-tail designs into the adenovirus vector and collaborated with the Volvax company that they are manufacturing. So we were analyzing the product in animal. So all these proteins made properly in the cell and in the supernatant, including the 4 head-to-tail RBD and the N protein. That's really amazing, included in a single adenovirus vector. You don't need to make nanoparticle. You don't need to make the scaffold protein and mix them together because it's very hard for quality control. So single adenovirus contain all of this, and then they have a 4 head-to-tail RBD that could present to the immune system. So what are the results? The results are very exciting to us because what you see is the 3 RBD on the top. The immunization is 2 immunization, 3 immunization. So what you see is on the left is the binding activity to SARS-1 RBD, SARS-2, and MERS. So this immunity induced has a very strong binding activity to all 3 human pathogenic coronavirus. And then in terms of neutralization, using this type of pseudoviruses that Susan just presented, you can see the neutralization titer against SARS-1 high, 10 to the 4, 10,000 ED50. MERS, 10 to the 4. SARS, SARS-2 wild type, alpha, beta, gamma, delta, BA1, BA2, BA5. All of them above minimum, above 10 to the 3. Some are really, really high. So suggesting single construct through intranasal immunization, you could induce a systemic antibody response against all those viruses. That's why we feel very excited. And then since the emergence of those very tough viruses, like a BQ1, BQ1.1, XBB, XBB1, we also use their serum to neutralize the viruses. As you can see, they also demonstrated 10 to the 2 neutralizing activity in those immunized with full head-to-tail RBD. And then those are simply the repeat, suggesting we are able to induce a good number of neutralizing activity against whole panel of SARS-CoV-2 variants, as well as SARS-1, MERS-1. Since this is a intranasal immunized, and then the question is whether they are able to induce a IgA response in saliva or serum. So you can see those with this detectable level of antibody response is all derived from either 3 head-to-tail RBD or 4 head-to-tail RBD immunized through intranasal route. If you immunize it through intramuscular, they are all below the detection limit, suggesting intranasal immunization is so critical in inducing the IgA response, not only in the mucosal surface, but also in the systemic, in the serum. So those responses are very impressive. However, if you immunize through intramuscular, there's no way you could detect it. So this is a very exciting data. And then we went further because we are not only measure the antibody response, we are also interested in the intranasal and lung T-cell response. So what we did was we collect the lungs and we isolate the cells, and then we measure a particular group of T-cells in the lung that's bearing a CD69 and a 103 marker that's indicative of a tissue resident memory T cell. Those are the effector cells play a fundamental role against the viral infection. So what you see, all those intranasal immunized has substantial higher level of T cell response, CD4 in lung, compared to the intramuscular immunized animal. And then for CD8, the differences are substantially higher, particularly for the 4-HT RBD, right? Suggesting there's something really special about the way of the design, about the way of administration. And then we went to have a very special surgeon to collect the nasal-associated lymphoid tissue. It's right just above the nose of mouse. It's very tricky because it is a very precise surgical procedure. So what you see is really the intranasal. You see all those detectable cells are all through intranasal induced. And then the proportion of those could be as high as 60% of the CD8 T cells. So it's really amazing. So what we're seeing are basically a black and white differences that through a intranasal immunization, you are not only able to induce a mucosal antibody and the T cell response, but also the systemic antibody response. So this is what we are, where we are. And then we are collaborating with a company for manufacture and also for the animal protection experiment in Singapore and in China. So the conclusion based on those exciting results, so we think that based on the structural functional study of spike RBD and antibodies, we have designed and evaluated a novel candidate vaccine not just against SARS-CoV-2, but SARS-1 and MERS. So it's very broad. We also think that intranasal immunization induces broad and potent neutralizing antibody and the T-cell resident memory cells that's really playing the fundamental role in attacking the invading bugs in lungs and the nasal lymphoid tissues. So we had some preliminary data already came out. That preliminary animal experiment demonstrated strong protection against beta and the Omicron BA.1 in mice. Well, against SARS-1, the MERS are underway because nowadays they're getting the facility to do SARS-1 challenge and MERS-1 challenge are very challenging, apart from my collaborators in Singapore and China. And Stanley, unfortunately, he's not here, but his facility could do the same. So while we're very happy with where we are, but we still have many challenges ahead, not just for us, but also for the whole field to evaluate the protective efficacy of intranasal vaccine. So down to the marker, we think that the biomarker with the clinical protection still need to be evaluated. David, you are the expert, so we'll seek your advice as what level would be needed, right, for clinical protection. That's critical because now the antibody are very correlated, serum antibodies, but mucosal is another whole new world. So the conventional parameters of circulating antibody, B and T cells, of course, will do it. We will continue to monitor the classic immune responses. But what about mucosal IgA, IgG in saliva, nasal, bronchial alveolar lavage, right? Or the tissue resident memory T cell, they are important, but they are not very easy to do. So for ordinary laboratory, for the general public, maybe we need to devise a better strategy to evaluate the mucosal immunity, so could provide a better associate or biomarker for the intranasal type of vaccine. Okay, so with that, with the work still ongoing, and then I have to express the sincere thanks to all the students, like the students sitting in the audience. They have done the tremendous work from the beginning of the pandemic. And then given the current situation in China, they are still working to push the project I have been telling you. And then with that, thank you very much again for your attention.
Gracias. Thank you very much for Linchi for the talk. Very nice. So I have a few questions. So this is very sensitive. Can go further. So if this RBD region is a good candidate because there's no mutations in it, does it mean that that you would really? I'll put the question another way. Is there a way to stress the system to see if in the long term the virus will be able to mutate the RBD region and those targets that you are actually currently using for these antibodies? Or is there some guarantee that the region is so important structurally that there's no space for future mutations? Yeah.
Those RBD that we designed, we cut off the region that have a flexibility to assemble to the native structure. So it's very important. Cannot change the structure, otherwise it's not going to generate a good response. But I have to say, the region we include those mutation sites. So it's not like without mutation. They include many mutations. The reason we would like to put them with SARS-1, 2, MERS, and Omicron is because if you present those to the immune system, they will generate some of a cross-reactive immune response that may offer the broadness, the breadth we would like to see. Because in previous publications, very interesting, if you were infected by SARS in 2003, and then boosted it with SARS-CoV-2 mRNA, you could generate a high level of broadly neutralizing antibody. So that's cross-reactivity, cross-priming, boosting, somehow boost a broadly neutralizing antibody. That's why we want to put a diverse RBD into the same construct. So when the immune system recognizes it, not just recognize one, but recognize several. So they may improve the likelihood of broadly neutralizing antibody.
Yeah, no. So, okay, so in other words, I mean, the specific regions that are conserved within the RBD that has several mutations.
They include the variable regions, but also include the
Yes.
conserved regions.
So those conserved regions, are they conserved because so far the immune system never sees those or rarely sees those regions, or because structurally the virus cannot change those regions?
That's a very good question. I think both. I think they are functionally very important because RBD have to form a certain structure. Otherwise, it would not be able to recognize ACE2. And then many of the broad, so that's reason one. The reason two, we know through the structure study, we know many of the broadly neutralizing antibodies recognize the hidden phases of RBD. Hidden phases, by hidden phases, not 100% hidden phase. It's a transiently exposed. It's only when RBD in a very standing up position try to grab ACE2 and then it got exposed. So those regions are very conserved. Antibody recognize that region are very broad.
It's like, so there's some, you're the right person then, because it has some similarities with GP120 in HIV process, right? Infection,
Yes.
where you have the binding of one first ligand opens or reveals other structures, epitopes that are important and conserved.
Right.
The other question I had is whether these immunization assays, whether you have performed them in an animal previously vaccinated with any of the current COVID vaccines to see whether vaccination will also shift the response toward mainly some regions in the RBD and not necessarily those that we wish we could
to have.
Right. Yeah.
That's the experiment is being done. Because we have all the different vaccines as a prime, and then come with a booster to see where that drive the response. So that's a very interesting experiment. What we do see though, if you using all the current vaccine intramuscular, and then come with the intranasal booster, the heterologous prime and boosting, that it give you very, very strong antibody and T cell response. Yeah. So this is, I think this is the way that the current intranasal vaccine has a good promise for even booster a better response, regardless your mRNA or inactivated priming.
Thank you, Linchi. In terms of the same question that Pablo was asking, this heterologous vaccination and routes of administration, have you tested the durability of the antibody response?
The response to RBD.
Right.
So after challenge or after booster.
After boosting.
Yeah. So we have not doing the detailed antibody analysis yet. But what we are planning to do is, because their antibody is so broad, we are isolating the polyclonal antibodies from the serum. And then we mix with the tetramer, we mix with the spike trimer. And then we could see it under electron microscope to see where those polyclonal antibody bind. And that's one way of doing it, because this is require high technology, high electron cryo-EM infrastructure. Another way we're doing it, we just simply clone the monoclonal antibody from those immunized animals to see where they recognize. We could easily test where those antibodies generated, and then give us some evidence or support to this strategy move further. So very exciting. Those antibodies may be super antibodies, right? So it's able to neutralize all those viruses. That would be great.
That's what everybody wants done.
Yeah, that would be excellent. So far, we are lucky. We are lucky to the step before the MERS. We have antibody that we are able to neutralize SARS-1, all the SARS-2 variants, including SBB and BQ1, from nanobodies or naturally infected human. Very potent, but it's very rare. It's about 1 every 500 antibody. We could get one of those. Yeah, very interesting.
Exciting.
Yeah.
Agradecemos al doctor Lin-Chi Chang por su presentación. A continuación los invitamos a un breve coffee break en las afueras del salón para reencontrarnos aquí en 10 minutos más. a la última charla de este simposio, que corresponde a investigación básica epidemiológica y aplicada en norovirus humano en la región de Antofagasta, a cargo de la doctora Margarita Lai, profesora asociada de la Universidad de Antofagasta y directora del Centro de Investigación en Inmunología e Inmunoterapia, también de la Universidad de Antofagasta. Invitamos a la doctora Lai a acercarse al estrado.
Thank you. Also, I will give the talk in English. Yes, for you. So, today we're going to talk about basic epidemiological research and apply in human norovirus in Antofagasta region. Next. Oh, sorry. Okay. Well, I don't know if you are familiar with human norovirus, but basically it's the main cause of gastrointestinal disease worldwide. As you may know, acute gastroenteritis causes one of the highest rates of morbidity and mortality in the world. And as a fact, human norovirus causes each year in the world 699 million cases of acute gastroenteritis, but also, unfortunately, 219,000 deaths per year, but also cause a huge economic loss that is estimated around $60 billion. However, there are no commercially available licensed vaccine against human norovirus until today. And as I say, this is the main etiological agent, which is no bacteria, that cause this gastroenteritis, acute gastroenteritis. And this virus affects people of all ages. And also, is one of the main characteristics is that can cause outbreaks in semi-closed places, as a kindergarten, as hospitals, homes for the elderly, and also you have heard in the news that cause outbreaks in the cruise, and also military residents and some social events such as wedding. So you need to be careful in the weddings. And also may cause sporadic cases, especially in countries in developing. So what are the main symptoms that cause human norovirus? Basically diarrhea, vomiting, and abdominal cramps. It has a short-term illness, it's around 28 to 60 hours, but a longer illness can happen also in immunocompromised individuals and can cause dehydration and hospitalization and can cause fatal infection, as I mentioned earlier. And the shedding, the viral shedding, the peak can be reached around 1 to 3 days upon the onset of the disease, but can be shed for up to 56 days, almost 2 months later. And there are many asymptomatic infections, and the main transmission route is the fecal-oral aerosol vomit. And this is a very contagious virus, and it requires only low infectious doses between 18 to 1,000 viral particles. As I say, the main transmission route is also person to person, but also through vomitus and through droplets. And also have been contamination by food, water, and also environmental. What is the characteristic of the human norovirus genome? in general? Well, this is a virus with a single-strand RNA, around 7.7 kilobases with positive sense, and has 3 orbs. It's not like a SARS-CoV-2, which is, or the pox virus, which are much bigger viruses. And it's very simple virus, even though can cause a lot of trouble. And basically, ORF1 codified for 6 different non-structural proteins, and ORF2 codified for the main structural protein, which is BP1, and ORF3 codified for the second structural protein, which is BP2. And basically, as you may know, non-structural proteins are involved in replication and pathogenesis of human norovirus. And basically, this is the structure of this norovirus prototype, which consists in 180 molecules, 90 dimers, and consists mainly of BP1, which is the structural protein as mentioned before. And this is a macrography of BLPs, which looks like also, why is called, well, because this norovirus belongs to the family of calicivirus, which looks the shape of a calyx shape, and this is why it was named calicivirus, and this is, I'm going to talk now. Basically, there is the classification of calicivirus and norovirus. Calicivirus has different genogroups. The one that we're going to talk now is norovirus. And it's known these days that the 90% of human norovirus infections are caused mainly by the genogroup 2. Today, it has been reported until 10 different genogroups, but the genogroup 2 is the one that causes the main infection in humans. So also the classification of norovirus is a little complicated because this is a virus that undergo different modification in the capsid. So in the beginning, it was classified the norovirus based on the capsid, which is BP1. So there are classification based on BP1. However, as I say, this virus modified the BP1 structure very easily. So later on, there has to be also classified based on the polymerase. So there are 2 kind of genotyping, which is called dual genotypification, one based on BP1 and one based on the polymerase. And actually, the G2, the genogroup 2 is subdivided into 27 genotypes, and it has been reported that the genotype 2.4 is the most prevalent worldwide. And also it has been shown up pandemic variants of G2.4 that emerge approximately every 2 to 3 years. As you can see, at least has been reported since 1974. It has been different pandemic variants that have shown up during the last decades. And the last one it has been presented is the Sydney, that has been lasting until these days. Well, so one of the studies that we want to do in our lab specifically do the genotyping of human norovirus strains in the population of the city of Antofagasta. And this work was done by Ms. Andrea Marcela Avellaneda Jimenez, who is present here, or it was here. Oh, I think she left, but she was here. And she's a master's degree candidate for biomedical science program in our university. And actually, the region of Antofagasta leads diarrhea in the country. Nobody knows why, but that's the fact. This is come from epidemiological studies or surveillance studies along the country. And it has been shown that actually the highest rate of incidence of this diarrhea happen in our city. So also this has been shown in different medias, and it's a concern of our region that there are a high number of diarrhea, especially in children. So also there are another problem because the surveillance in our country for norovirus has been very deficient because mainly has been detected or have been screened for rotavirus and adenovirus. Rotavirus, as you may know, also before that the two vaccines came out to prevent this infection for rotavirus. Rotavirus was the leading virus to produce diarrhea. But after these two vaccines came out, norovirus is the leading virus that induces acute gastroenteritis. So many of these different places that we call SFAM, which is the health centers basically, and they in charge of this surveillance, have a screen only for rotavirus and adenovirus. However, as you can see, most of the cases are negative, more than 80% are negative when they do the search for these two viruses. So our research hypothesis is that genogroup 2 and the genotype 0.4 genotype Sydney variants of human norovirus predominantly affect young children with acute gastroenteritis treated at the Hospital Regional of Antofagasta. The general objective is to determine whether genogroup 2, genotype 0.4, and the human norovirus Sydney variant predominantly affect young children with aged care for at the Hospital Regional of Antofagasta. And basically, the specific objective is to determine the genogroup 2 is the most predominant genogroup in this population, and also to identify whether the genotype 0.4 human norovirus genotype and Sydney variant is the most prevalent in this young population. And this has been done through qPCR, the first aim, and the second through RT-PCR and genomic sequence and the use of the NoroSur platform in collaboration with the CDC of the USA. So basically, we have taken the general methodology consists in taking the sample from the hospital from patient less than 5 years old with viral acute gastroenteritis norovirus positive by immunochromatography. And then these samples were analyzed in our laboratory, Advanced Molecular Virology Laboratory of our university. As I say, these were analyzed by RT-PCR, sequenced, and also analyzed in the NoroSur platform, and then the genogroup was determined by qPCR. Well, this is the methodology a little more in detail. And one of the objectives consists in determine the genogroup, and the other objective is to consist in identify the genotype and also the variant. Basically, the primers that we use, they can amplify the region B, which is in the ORF1 of the genome, and also in the upstream region of ORF2, which is called Region C. The results of this analysis, basically from 185 samples, we got 64 positive, 64 were samples from 5 years, less than 5 years old. And we got from this 119 population, we got 51, so the 43% of positive sample for norovirus by immunochromatography. And that is the distribution of by sex. And this study was carried out from January to December the year 2019. As you can see, the samples that we analyzed basically showed that the norovirus show a peak between the months from March to June, and the other gastroenteritis acute negative samples appear in the rest of the other months of the year. And as we also raised in our hypothesis, most of the samples result to be genogroup 2 of these norovirus positive samples. This was published in Emerging Infectious Disease in 2021 in collaboration with the CDC. But we also have analyzed that, very interestingly, that is in Spanish, a patient less than 1 year old, most of the norovirus positive cases were children that were not hospitalized, and the 37%, the less percent, were hospitalized. However, patients between 1 and 2 years, it happened the opposite. Most of them, 62%, happened to be hospitalized children, and the 38% were not hospitalized. In patients between 2 and 5 years old, most of them also were hospitalized. So it appeared that when they are less than 1 year old, they get some protection, most likely through the antibodies that receive from the mother. And a very interesting result that we got is that most of the samples result to be also genotype 0.4 in most of the sample, basically the 95%. Also, this was published in the Emerging Infectious Disease. And also, as a result of the dual genetification, we found that most of them result to be genogroup 2.4 New Orleans and genogroup 2.4 Sydney. As I showed you, is also follow what we thought in our hypothesis, and also we found a combination between G2.P16 and G2.4 Sydney. But most of them result to be G2.4 Sydney, as the literature shown in the rest of the world. So this work was published, as I say. This is part of the collaboration. This is the result of the whole world, that the CDC has collaboration in different parts of the world. And so we were the reference of our country and also part of South America, and basically result to be also most of them G2.4 Sydney, as was predicted. this is the publication that it was in 2021. So in conclusion, human norovirus genogroup 2 was the most predominant stool sample from children less than 5 years old, with the hospital of the regional hospital of Antofagasta with viral acute gastroenteritis in the year 2018, and a greater number of severe cases observed in children older than 1 year than those less than 1 year. And human norovirus G2.4 is the most prevalent, 90.5, and human norovirus positive stool sample from children less than 5 years of age. And human variant G2.4 Sydney was most predominant and also in these samples in children less than 5 years old in the hospital regional of Antofagasta with undergoing acute gastroenteritis. So as the other expositors show, it's important to do a surveillance. For what? Why is important to do this surveillance? Because we want to have a very precise design for a vaccine that can protect us from these viruses. So this work that we want to design a vaccine, taking this information that also we did in our region and in our country. This challenging took it another student who was a biotechnology undergraduate thesis student, Miss Claudia Campillay. And the name of her thesis is a study of immunogenic target for the design of a vaccine against norovirus G2.4. Basically, why we don't have a vaccine available for human norovirus nowadays? One of the main problem is that the animals susceptible to norovirus, we don't have a small animal model. The only animal model that we have available are the piglets and also the monkeys, not human primates. And basically also there has been for many years the lack of a cell culture system that is easy to implement in laboratory, and a permanent generation of new viral variants short-term and also that become in a short-term immunity. Well, and also has been many investigators have tried the design of classical vaccines, basically inactivating or live vaccines with that reduced virulence. Another disadvantage of classical vaccine is a low biosecurity due to virulence reversal, and also is inefficient in cultivation of pathogens, and also the appearance of allergies and autoimmunity. In contrast, we have another proposal, which is the epitope-based vaccine. So basically, this vaccine can provide a specific short regions, high specificity that are conserved, security, and can be also easy to produce, storage, and can be stable. So basically, these are the vaccine types that have been tried until now. Basically, based on BLP, as I shown earlier in a slide, that basically is based on BP1. And one of the norovirus, and also, sorry, they are the one that were based on adenovirus recombinant, and also and based on the particle P, which is part of the structure of the BP1. And basically the norovirus genotype include genogroup 1 and genome 2.4. And many of those, but as I say, all of them, the most of them based on BP1. And the route of administration basically has been intramuscular, that here one intranasal, similar as the proposal or our previous the doctor. And also in what the different phases that we have in each of these vaccine candidates is mostly preclinical studies, and there are some that one based on VLPs in phase 2, and one of adenovirus in phase 1. And well, they have been in different, developed in different institutions around the world. So, however, there are no structural proteins based in human norovirus vaccine formulation. And so we want to explore that possibility. So we raise an hypothesis that conserved sequence of non-structural proteins belonging to variants of human norovirus G2.4 possess immunogenic antigen for the design of a vaccine against this virus. So the general objective is to assess whether the amino acid sequence of non-structural proteins of human norovirus G2.4 possess highly immunogenic antigens. And the specific objective that was want to Miss Claudia want to perform is first perform amino acid sequence analysis of the non-structural polyprotein of human norovirus G2.4 variants. The second, perform a predictive analysis of immunogenic epitopes and conserved region of non-structural proteins in human norovirus G2.4. And finally, make prediction of antigenicity, allergicity, and toxicity of candidate epitopes for incorporation in a vaccine design against human norovirus G2.4. So basically, this is the general methodology. Well, this is a very complicated bioinformatic analysis, but basically, the aim one consists in the sequence collection and analysis using different programs, but basically the sequence that was already published, basically in the NCBI data, and also was Eugenius and the protein variability server programs for the prediction of conserved sequences. And the aim two consists basically in epitope mapping, and also was used different bioinformatic programs to basically determine antibody binding epitopes, and also interferon gamma induced epitopes, and finally to obtain MH class 1, human MH class 1 and human MH class 2, but also that coincide with regions for mouse MH class 1 and mouse MH class 2 binding epitopes. And finally, in the third aim consists in the selection of potential candidate antigen epitopes, which, as I mentioned before, basically using these bioinformatic programs can be determined the antigenicity, the allergenicity, and the toxicity of these epitopes. As a result, basically, it was obtained a phylogenetic tree based on the protein sequence of human norovirus G2.4 variants collected from the NCBI database. Claudia basically aligned around 45 different sequences of genotype 0.4 norovirus. And from this analysis, basically, we got 5 different epitopes of MH class 1 binding epitope selected by this bioinformatic prediction that basically has, it's also in Spanish, binding of antibody, also has an induction for interferon gamma, is antigenic, is no is allergenic, and no is not toxic. And also the alleles also can be tested in mouse, being consigned with the human alleles. Oh, so that was for MH class 1, and for MH class 2, we got similar results. And in this case, Claudia got 16 different epitopes. And also these epitopes belongs to different non-structural proteins. So basically, we want to finally, the conclusion of these results is that the conserved sequence of non-structural proteins belonging to the variant of norovirus G2.4 possess immunogenic antigens for the design of a vaccine against this virus. 13 MH class 1 binding epitopes were obtained. 5 of the predicted epitopes could induce a humoral and cellular immune response mediated by CD8 T cells. 8 of the predicted epitopes could induce a cellular response mediated by CD8 T cells. And also was obtaining 16 MH class 2 binding epitopes. From those, all the predicted epitopes could induce a humoral and cellular immune response mediated by CD4 T cells. And all these epitopes could be tested in a mouse animal model. So the future direction for this work is to develop a candidate vaccine formulation containing the immunogenic epitopes of conserved region of non-structural proteins of human norovirus G2.4 with an adjuvant, and also immunize mice and evaluate the safety and immune response generated by this human norovirus G2.4 candidate vaccine. And also we want to evaluate the protection and efficacy of human norovirus G2.4 candidate vaccine against a challenge by the most prevalent human norovirus worldwide in a susceptible animal model. And to evaluate, and this is a different project that we want to do alone, which is to evaluate and determine the effect of human norovirus infection on the intestinal microbial, but not only analyze the bacterial profile, but also the fungi profile. So the microbial structure in patients with acute gastroenteritis through the sequencing technique. And also we have some preliminary results because we also have studied the prevalence of human norovirus genogroups and genotypes in kindergartens and epidemic outbreaks in Antofagasta region. Basically, to do so, we have collected sample from 3 different children care centers and also from diarrhea outbreaks that actually, he also was here. He left. Well, the person, Javier. Javier helped us. He was the chief of the epidemiology of our region of Antofagasta, and he provided us the sample from outbreaks, from diarrhea outbreaks. And with this similar analysis as I showed before, basically we determined the genogroups and also the genotyping. So basically, and this is the work of a current biochemical undergraduate thesis student who is Miss Nelly Olivero. She actually showed this work in the congress that is going on right now in La Serena. There's the Society of Microbiology of Chile. And basically, she showed that most of these samples were positive for human norovirus. But they also showed that most of these samples from the stool sample from children less than 5 years old attending these child care centers was positive, around 68% were positive for human norovirus, and most of them, the 81%, actually corresponded to genogroup 2, and the 19% correspond to co-infection between genogroup 1 and genogroup 2. Okay, and these include symptomatic and asymptomatic children. And another person, part of our team, who is a research assistant, she's a biotechnologist, Ms. Chelsea Cuellar, also helped to identify the genotyping in these children attending childcare facility, also in people affected by diarrhea outbreaks in Antofagasta. So as she could find out, basically the most of the samples, this is the sample from the outbreaks, and this is the sample from a child care center. Yes, most of them corresponded to genotype, again, genotype 0.4 based on the capsid, and genogroup 1 and genogroup 2, this is based on the polymerase. So basically found as a genotypes, genogroup 1.1, which is actually the prototype norovirus, which is called Norwalk virus, and also found genotype 2.4 also in these samples. And basically also found the genotyping based on the polymerase, found all these different genotyping. Some of them, they were not typable, maybe because it's a new variant that in that case we need to sequence the whole genome to see if it correspond to a new variant that can be also reported. We can do it later also, some studies to sequence the whole genome of all these samples. But basically, most of them were genome 2.4 and genogroup 1.1, and we found P16 and P4 and also P1. That has been reported also around the world. So with that, I want to acknowledgement, well, our team, which is the Atacama Desert Vaccine Laboratory, who is Dr. Cristian Muñoz, who is the director, Dr. Angelo Retamal, who is the investigator, Professor Ninfa Williams, who is the administrative management, and our collaborators, Dr. Alexis Calergis, Dr. Susan Bueno, Dr. Pablo Gonzalez, and our postdoc, Dr. Valeria Garcia, the professional Chelsea Cuellar, who is the research assistant, and the student Andrea Marcela Avellaneda, who is a postgraduate student. And basically, we are very grateful that you came today for this kickoff of our laboratory, which is the Atacama Desert Vaccine Laboratory, and we think that this is a very important an important day that we started to develop and create new tools to find to these different infectious disease, and also to form these different students that they need also a platform, a center where they can also study and develop the research. Well, I also want to acknowledge my former students and my present team members. And also, I want to thank Dr. Jan Binche, who has been collaborating with us. And here we join and we met in the calicivirus conference that happened in 2019, also in Sydney, Australia. And also, we like to say about our center, which is was created last year, is the Center for Immunology and Biomedical Biotechnology Research Antofagasta. Basically, this center is a platform for scientific collaboration, and basically, this center can work different experts in immunology, virology, microbiology, parasitology, cancer, and biomedical biotechnology of the University of Antofagasta, the Catholic University, the University of Chile, and the Millennium Institute. All of them participate in this center. Our mission basically consists in to carry out research of excellence in immunology and biomedical biotechnology with focus on the development, innovation, and elaboration of quality biomedical biotechnological solutions, including vaccine, and with the highest technology to prevent and reduce disease that affect the health of the population. Our research line basically consists in development of vaccine therapies and detection methods for viral and bacterial human pathogen, but also studies of the immune response to viral and bacterial infection, parasitic disease studies, and the identification and characterization study of molecular marker and therapeutic target of no-infection human disease as cancer. Our team are basically are part of the Atacama Desert Vaccine Laboratory team, but also there are other experts like a Dr. Jorge Gonzalez. He's an expert in parasitic infection. Dr. Mariela Rivera, expert in viral and bacterial genomic sequencing, similar as Dr. Paris Levine, who is also expert in microorganisms from extreme environments such as Antarctica and also the driest desert on the world, the Atacama Desert, for biomedical application. And also Dr. Alexandra Galetomic, who's an expert in metagenomics for diagnosis of pathogens and cancer. And also she participated in genomic surveillance of SARS-CoV-2. And also we have another expert in cell biology with focus on parasitic infection, and another expert in physiology and cell biology with a focus on cancer and diarrhea. And our national collaborators is Dr. Calergis, as you know very well, Dr. Susan Bueno, Dr. Pablo Gonzalez, and Dr. Leandro Carreño, who are all of them, except for Dr. Alexi here. And we have an international network of all the SIVA members, have different international networks around the world. And hopefully you can also join us to these international networks one day. And actually, this is the Coloso campus of our university. And this is, this is southern part of Antofagasta. Here is the sea, and this is the main highway of our city. And so part of this campus have this area that we are projecting to build a building around 1,000 meters square of 3 floors to build the SIVA Center. So hopefully in the future you can also visit this new facility. So with that, I want to thank you, all of you. I don't know if you have any questions o preguntas. Okay. Well, thank you very much. And thank you for our speakers, the national and international speakers to have came today. I don't know if Dr. Cristian Muñoz or Dr. Angelo want to give the final words.
Muy bien, agradecemos a la doctora Margarita Lay por su presentación y a nombre de la Universidad de Antofagasta agradecemos a todos y todas las presentes, a los speakers que concurrieron hasta nuestra universidad por su asistencia y nos vemos muy pronto. Muy buenas tardes.